Alright, hell yeah. So we have a statics problem, and we just did it. We probably spent 5 hours on this. And so here was a problem sent in by a German student, and pretty cool, because this was fun. And so my videos are for entertainment purposes only, and educational, I would say. So I do long videos, kind of just ramble, but we go over the nitty-gritty of problems. And I do this from my perspective. And, you know what I mean, once you do a problem, sure, you can go back to it and do it, like, precisely and fast and all that. But leave a like and leave a comment, you know what I mean? I feel like I might be one of the only ones that do long format videos where I just don't even care. And you come from a perspective of just like, sure, you feel smart, but yeah, no, like learning stuff is a slow process. And I'm going to take the slowest process ever and slow roll a problem so I can always kind of grind. I remember in college, you're just like, nah, can't do that. Maybe I'll just put it aside. And maybe by osmosis I'll come back to it. And sometimes that works, but I like to find solutions where it's just like, yeah, sure, there's stuff that's I think I don't know, but then we come up with like graphical solutions and we actually get answers. So I'm not going to give anything away in this problem, but I think it is a worthwhile one to sit back, relax, and enjoy. So anyway, without further ado. Alright, hell yeah. So we have a statics problem. This is a German student who is taking statics, so engineering mechanics. This is the Hibbler book. Now, their professor just kind of does problems like these. They, you know what I mean, you have resources like a textbook, like Hibbler, you know, just kind of as a generic. Most of the problems are kind of generic, but this professor really challenges the students with problems that you aren't going to find. And it's really good because then you don't have a, you know, you might not even have example problems in this book where you're just, I don't even know what's similar to a problem like this. But what happens with statics problems is they can get complex where maybe you're not able to solve for everything. You know, I mean, it gets into the realm of like, okay, I got to solve for 3 different things, whether these members have tension or compression, and then a magnitude, you know what I mean? So we want to find, we have a 500 Newton load in kind of American, let's say it's just, what would that be? I don't know, like 1,000 pounds, you know what I mean? Close enough. So just in general, we got something that can carry 1,000 pounds, and we have this structure. What was I getting at? Is that cool? And we just wanted to know, like, hey, like, what's the, sometimes, you know, you could have leverage where maybe there's 10,000 pounds. That's kind of the first thing. So let's dive into that, because some, especially problems where you're just like, you know, I would, if I was to build this thing, would I be like, oh yeah, I'm just going to measure 5,000 millimeters? Hell no. So that's going to be, so everything's in so that's 5 meters, and I'm an American anyway, so I don't even know what 5 meters is. So I just do 5 times 3, 15 maybe, and you know what I mean. So we got 15 feet. Okay, so now I'm really trying to visualize this of like, hey, what could this thing be? And so we got 15, another 6. You know, we got 20 feet this way, and then maybe about the same. Yeah, and hopefully it's to scale. So yeah, we got 20 feet, maybe 18 feet, maybe 20 feet this way, you know, bottom to top. Cool. And this is about 15 feet. This is about 6 feet. Cool. And then for this problem, the weight of this thing is negligible. So maybe this is just a lightweight steel frame. That can still take 1,000 pounds. You know what I mean? You can be pulling 1,000 pounds on it, and yeah. So anyway, so let's dive in, because the other thing that I wanted to do was like I just got this. I haven't looked at it at all. The student actually wrote a bunch of pages that I don't have printed out yet about his solution. But the first thing that, you know, I see is this is always kind of confusing. where let's say you were just hanging the load just from a point, like 1,000 pounds, like that's what the load would be. But then the second you wrap it around a pulley, and this is a good strategy for like, hey, how to make a problem simpler. We're wrapping this around a pulley and then coming at an angle. So let's just take it so we're pulling from the ground and then going around a pulley, and then we have 1,000 pounds. Okay, and then this is kind of an interesting scenario where it doesn't feel like you're getting leverage, but hell yeah, you're getting leverage. From this pulley, it's like you're pulling twice as much. So you would have that free body diagram of that pulley would be 1,000 pounds down and 1,000 pounds down on this side. Cool. So you're literally pulling 2,000 pounds down. So you could, if this is the corner of that box, you could just say, hey, there's 2,000 pounds on it. Cool. All right, so, and let's do that. Let's just say we have 2,000 pounds. Well, I guess we can do newtons. Sorry for going into pounds. I think newtons. That's everyone knows newtons. Even if you don't have like something similar. Cool. But anyway, I need to slow down a little bit. Okay, so we have 5,000 newtons hanging off this box. I'm just going to say it's 10,000. So we're going to have 10,000 newtons hanging off this corner. But because this is a 45, that's the other, like, it's good in statics to look at an angle and be like, okay, I'm going to have 1,000 pounds down here, and I'm going to have 1,000, I'm sorry, I shouldn't have even said 1,000 pounds. This load is 5,000 newtons. Because it's wrapped around a pulley, the tension in this cable is going to be 5,000 newtons. So we're going to have 5,000 newtons down this way. So I guess I can just kind of draw that. 5,000 newtons. And then we're going to have 5,000 newtons this way. Yeah. And that's the thing is, like, I'm going to go over this problem kind of in a long format. And then maybe I'll do a separate video of how to do it. You know, like, what's the nitty-gritty? I think when you're looking at a problem like this, you're probably just like, well, what are the equations? What are the unknowns? And you can do these sometimes from a mathematical perspective, but I consider that like knowing, I mean, almost like a magic trick, where you're just like, oh, I'm just going to do it from a purely mathematical perspective, get, so many equations, so many unknowns, and make sure I have the same amount of equations and unknowns, and then just say, mathematically, it's going to work out. But it's kind of good to do problems from an intuitive perspective. So even right here, this is one of the classics where, okay, if I have 5,000 pounds being pulled at a 45-degree angle, how much of that is down, and then how much of that is that way? Because we can take this vector at a 45 and then break it into components that way and this way. And what you would have is, I like to think of this ratio of like 1.5. The square root of 2 is 1.4. You know what I mean? 1.414, or whatever. But basically just 1.4. And even if you guesstimated 1.5, you know what I mean? You're pretty good. Now, it's not, if it's 5,000 down your, this is your hypotenuse. So this triangle, your hypotenuse is always going to be the larger side. So if this is a right triangle, and just even the basics of statics is like, hey, I have this vector. It's 5,000 newtons, and I'm going to break it up into components. I'm starting here. I could go 5,000 this way. I mean, okay, so now the components are I can go this way down, and then this way over. Or I could go over and then down. Now, if this is my hypotenuse, the take-home point is this hypotenuse is always going to be the larger number. These are going to be the smaller numbers. So I'm not going to take 5,000 and multiply by 1.5. I think those are the very small and subtle tricks that are very useful in your head to be like, okay, I got 5,000 here. Well, obviously the components this way and that way are going to be smaller. And it would be easier if it was the other way. Let's say I knew that this was 5,000. a component this way over and then a component down was 5,000, then what would be the component down this way? It would be, I would just do a multiplication of 1.5, which then I could do that in my head. I would take 5,000 plus 2,500, and I would say this is 7,500. But to go the other way, it's a little bit harder. I have to take 5,000 and divide it by 1.5, and that's like, well, what's 1 divided by 1.5? So anyway, let's go over that, because maybe we can find a way to simplify this. 1 divided by 1.5. Anytime you got like, this could be a strategy of like rationalizing the denominator. One way is just, well, get this as a whole number, so that's going to be 3, denominator, the numerator becomes 2. Okay, so now taking this number and dividing by 1.5 is the same. I got to be careful here. Yeah, I got to be really careful here, because I'm starting to confuse myself. It is good. This is why I do these videos, because like if you can talk your way through something, sometimes you just like keep it going. But hopefully, and it's okay to make mistakes, because I don't know like how you're going to learn without just being like, hey, this is what sometimes I do this. It's just like, hey, I think I'm going to make a mistake. Put 3 asterisks on a page and then just go for it. I think what I want to do is say 5,000 times 2/3 is going to be my answer. I'm going to say 5,000 times 2/3 is the same thing as 5,000 divided by 1.5. I don't see it, but I know I got to divide 5,000 by 1.5, so let's try that. 5,000 divided by 1.5 is the same thing as 5,000 divided by, I'm going to say this is 3 times 2. Okay, so there I see it. So 5,000 times 2/3 is the same thing as 5,000 divided by 1.5. And sweet, so maybe I can do 5,000, well, yeah, I can just, 5,000 times 2 is 10,000, divided by 3, that's going to be 3,333. Now, a lot of people say, hey, get rid of your calculator, don't use it. Well, okay, well, settle in for like a 5-minute little tutorial on how to do something simple. But yeah, we're 10 minutes into this video, and all I'm going over is, you know, just taking how to take a hypotenuse and break it into 2 components, and do it so you can look at this and do that visually in your head. Be like, okay, 5,000. Now I can easily say this is 3,300 this way, 3,000, and we're just round. So we got 5,000 down here, plus another 3,000. So sweet. So off this point, we're going to be having like an 8,000 down, and then we're also going to have a 3,000 that way. So that's all we're doing is just kind of guesstimating and looking at this and seeing what's going on. All right, so I think the second aspect is of this, and we haven't even gone over like statics of like, hey, all the, like, why if I'm pulling down on this, do I need to balance it with forces this way that are the same? So let's talk about that for a couple seconds, a couple minutes. So what a free body diagram does is like, hey, you kind of chisel this box. And I like my way of doing it, of saying like, hey, what you're trying to do is just chisel this box and then maybe draw it on a separate sheet of paper and then just say it's the only thing in the universe. Like there's no other material in the universe except this box. Like there's no stars, there's no gravitational forces. But then you know like what the universe, is, you got a mass here, and then like what we know about, how things work is if I put a force down here, what do we say, 8,000 pounds, and then we got a 3,000 pounds that way. So at the end of the day, this is the base, this is the start of what we have, especially since this is the only thing that we kind of know that's happening to this box. So the fundamentals, like Newton's laws, are like, well, a couple things. One is that, cool, we now have a known force on a rigid body or a mass, and we have 8,000 in this direction. So what should happen to this? This thing should be going this direction, and it should be going that direction proportionally. You know what I mean? And, like a true vector, it should be going 8,000 this way, 3,000 this way. So it should be going this direction. But we know it's not, and that's the basics of statics. We know that, hey, so we drew a free body diagram. We at least know these two forces. That means it should be moving this way, and it should be moving this way, proportional to its mass. So let's at least write F equals ma. And we've identified a force. We know that this rectangle is our mass, and then this is what we output. Acceleration is change in velocity, change in time. So so if we get a number for acceleration, then we would know that this thing is going to change in velocity every second, in this direction and this direction. But we know we don't see that, and then the question is why? Well, we go back to Earth, and then we set up this experiment. We take a chunk of steel, and now these are like pivots. So we have like a chunk of steel on a pivot, and so it's kind of floppy. You know what I mean? These aren't rigid connections. They're just like hinges. And what do they say? Yeah, 3 hinge supports. So if you... so I think that's the other thing that I don't think students do, is just like, let's say you have this box, and we're saying that it doesn't weigh very much, but who cares? It's still like a thin metal frame. It doesn't have to be like enclosed in at all. But let's say we have just somebody welded up a rectangle, and then we hinged it to this rod, and then it's also hinged to the wall, hinged to there, and then we just let go. What would happen? It would just like fall down. Okay, sweet. So that's number one. The second thing that we're going to do is we're going to put this rod on it and then just hold it in place. The box still has some weight. It's very lightweight, but now what's going to happen? Well, it's probably, yeah, I don't think it's going to go anywhere. You know what I mean? Is it going to collapse or do anything funky? Nope, it's not, because it's going to be pulling down on this one. So we're going to have tension in that one, and then compression in this one. Now, probably if we go to our solution, that's not what we're going to find. I did take a look at the solutions, and it says that S1 is in compression and S2 is in tension. So yeah, and we're going to get to that in a second, because it's the... And, yep, that's the next place where I want to go. We should do probably one thing at a time. But hell yeah. Okay, so back to the basics. We have this rectangle. We have a force on it. The only way for it not to travel in this direction, we got to put a force somewhere. So let's take a look at this one. Cool. I mean, this is still hinged to the ground. If we just had this one... We have this square box, and this is hinged right there and hinged right there. So this thing would be very unstable. You know, minus even the load, it might just fall that way. You know what I mean? And if we put load over here, it's gonna rock this direction, and then probably just fall that way to the ground. But let's say it didn't. For whatever reason, forget the load. We put this rod right there. It's still balanced, but let's say the center of mass is just right there, and so this thing is just balancing on that rod. And so now back on Earth, what we see with this box is it's not moving. It's like totally stationary. And so now we're going to go back to our drawing. And in this case, these forces aren't there. We still have our box. We have this rod holding it up, and we just have the weight, the center of mass of this box is right there. So, I mean, these are just basics of statics, but it's good to go over all of them, because I think if you don't, then you're just going to be looking for equations and unknowns, and then I think... Like, even for me, like, I'm not doing this for you. Like, it really helps me to get faster at understanding the fundamentals. And I think it's important. Alright, hell yeah. So in this case, we would have the mass times gravity, which is the weight of this. So we're going to have a force, and this is the force due to weight, or the force due to gravity, and it's going to be pulling down. and we have this box as the only thing in the universe, and then we're going to have a force up, and that's going to hold, and that's going to be equal. So we have this idea in statics that, cool, we made this box, we know that it has a weight on it, and why would it have a weight? Is because it's made of mass and you have a huge earth underneath us. Now, our problem says, you know, neglect this weight, but I'm just going over the fact that it could have weight, and that's the first and easiest thing to look at with this box, to be like, well, how to draw a free body diagram. We're chiseling it out. We drew a box. And we said that it has this weight at its center of mass. If it has this, and the weight is a force, so maybe get just a fresh sheet of paper. If we have this box and we have a force on it, that's the W, or you could say force of weight or force of gravity, then this thing should be moving this way across the universe. And due to F equals ma, if this velocity is 0, if the box is at rest and you put it there in outer space and then you put a force on it, well, now it's going to have a change in velocity due to F equals ma. You put a force on it, that's the weight. It does have a mass, and then so we can calculate the number for acceleration. The number that we get here is going to be the change in velocity per 1 second. That's the definition of acceleration. Acceleration is change in velocity, change in time. Cool. That's going to be the change in velocity per 1 second if the units are in, like, you know, meters per second per second. Cool. And it's always good to write F equals ma and then rearrange for acceleration. We want to solve for acceleration, so you'd say acceleration is force divided by mass. All right, hell yeah. So what did I say that I wanted to do next? The next thing is just like, well, so back to our box, and we have 5,000 newtons down. Is there any reason why we would have one of these members see more tension or more compression than 5,000? It's like, that would be a pretty decent question to maybe ask, and it gets into the idea of leverage. So I think we can, the first thing with leverage, and it's good to do these problems where you're just like, well, let's take away this. So we're gonna take away this 45-degree angle. I don't think we need to, but just visually, we're gonna have this 5,000 newtons down, and we're going to have this pivot right here, and you could even just make it, you know, rigid if you wanted to, but being able to pivot off this point, and then we're going to leave this bar into place, because part of our solution is that this bar S2 is in tension, and maybe that's a question of like, hey, I don't see that, I want to know why. So we're going to get rid of this member, we're going to put 5,000 newtons down. Here's our pivot point. So if this is our pivot point, we're pulling down on this, it's going to be pulling up on that. It's kind of like this is a teeter-totter right here. So there you go. So we have a teeter-totter, we're pushing down, and if this is a rigid body where it's like, hey, I put a weight over here, but this thing's not moving, well, why? But maybe it's maybe you have a rope attached to the ground right here. So when I put weight down here, the tension in this rope gets hella, and that's because it has tension. Like this could be a rope then. You know, with this scenario, you could make this member just be a rope. Cool. And so we have the solution right here. And so this is our only member that can be a rope. S1 and S3 could be in compression. Now, for this problem, the students were given the question, the diagram, and the solution. And I don't know, sometimes this isn't helpful because it's just like, it maybe makes you go right to the equations, and if you're not, you know, getting these answers, I don't know, it's just it could be a long way away to get answers like this. And so we'll see how I do this. Sometimes I like to use like a numerical approach, you know, to get close. and then go back and see how to refine it, and see if just because the students said, yeah, this was a bummer for everyone in the class. You know what I mean? It was really difficult to see, to get the right answers, and so hopefully, we'll learn a little bit during this. But hell yeah! So that's the second point, was just like, hey, compression. So let's do a diagram. Let's get rid of this one. We have the 5,000 down, and then let's move this member. That's also a good thing to do, because we can see if we're generating more leverage or less. So I think it's going to be easier to just move this way and see that we're generating hella more leverage. Because if this point is right under here, then we have 5,000 newtons down. The teeter-totter's right here, and we're getting all that leverage. Because that's a property of statics. And even motion too. If you have a force at a distance, you're generating, more leverage or torque, where things are either spinning, but from a statics perspective, you're generating a moment. So that brings up the idea of like opening a door. You have your handle as far away from the hinges as possible, whether you're pushing or pulling. Let's say you're trying to open the door this way. So we have a force on the door. You have a distance out, and we use the equation that's F crossed R is going to be the magnitude of the leverage that you're getting. So moments are, moment of a force is, well, that's what like in general, when people talk about a moment, especially in statics, they're talking about a moment of a force. And so what is a moment of a force? It's and you could also say it's the first moment of a force, because we have a force times this distance, and the distance is to the first power. If the distance was to the second power, then you'd have the second moment of a force. You never really have a second moment of a force, but you might recall that you have second moment of mass, which is the mass moment of inertia is I is equal to mr squared. You're going to have a mass of something, and then you're multiplying it by r squared, which is also I is equal to m cross r. And it could be a vector. Vector of a mass times the vector of the distance, and you're squaring that. And but mass is not a vector. It doesn't change with any sort of direction. It's a scalar. So you just have, but for this quantity, it's the second moment of mass, because you're multiplying it by the distance, but the second moment part is this squared. So anyway, so you have moments are first moment of force, and it's just the force times the distance. Only if this is a perpendicular. If you're trying to open the door by pulling perfectly that way, where your angle is 180, or what we would just say 0, you're not going to open the door at all. So you have a hella force, and you still have this distance here, but because it's the cross product, the scalar is this force times distance and then times sine of the angle. So if your angle is 180 or 0, this becomes 0. And if you have a 90-degree angle, sine of 90 is 1, and you're basically get 100% of the juice with leverage. All right, hell yeah. So if we put this pole right here, we're going to be getting, all this force times that distance, and that's going to be leveraging it. We can draw a teeter-totter where, you got someone heavy over here, and then you put the pivot right here, and then you, just put a string to the ground again. Hey, hell yeah. This is how you can put a ton of leverage into this string. And this could be like 10x, because this distance could be 10 times the distance of, this is 1 times the distance, this is 10 times. So you get a leverage. And what did we say moment was? it's a force times distance. So we have W times 10x, and then over here, that's the leverage we're getting, and that leverage has to be resisted by this leverage, which is the tension in the string times 1x. So we have tension times 1x is equal to that weight times 10x. And so if we wanted to solve for the tension, we would have W 10x divided by 1x, and we would have 10 times the weight. So the tension in this string is 10 times the weight. So there you go. So that's all I wanted to go over for these problems. You could get a numerical answer. You know, if we throw in, yeah, so if we, and, you know, man, I have a, so square root of 2 is, let's say, just 1.5. And then we have, and this is going to be 4 divided by 4. So we have 1.5 plus, and then we got 5 divided by 4. So sweet. So we already have we already have 1.5 plus definitely more than 1. So we got like 2.5 for sure, or close to it. 2.5 times the load. So hell yeah. So we already have 2.5 times 5,000, and that answers my question. So we'd have 10,000. We would have 12,000. So about 12,000 newtons could be the tension in this cord right here. You know what I mean? If this was a rope. You know, due to just the layout of this, you know what I mean? You're pulling down over here, and off this pivot point, you know, you're leveraging this. Cool. So now, if I'm leveraging it, is there any reason why this member should be like astronomically large or low, or will this will the compression in this member, like, I don't even know, you know what I mean? Is this one going to be fairly close to, yeah, it's kind of interesting. Well, let's just do a little example. So if I'm going to pull down with 5,000, but I'm going to push up, no, is that right? There's tension in this. Okay, so if there's tension in this cord, it's like I'm pulling down. Yeah, so I'm gonna be pulling down with 5,000 here, and I said I'm gonna be pulling down with maybe like 10,000. So definitely more, due to this being the pivot point right here. Cool. So sorry about my arrows, but we have 10,000 down and 5,000 down. So if that's the case, if I do a free body diagram, this is the only thing in the universe. I'm pulling 5,000 down here, and I'm also pulling 10,000 down here. Then hell yeah, I must have to put a force this way. And it goes back to F equals ma. The free body diagram says, hey, I built this frame, and it's the only thing in the universe. But then I'm putting known forces on it, 2 in this direction. It's going to travel in this direction. But I go back to Earth, and I'm like, whoa, this thing isn't moving at all. It's not moving this way, this way, this way, this way, or spinning. That's the definition of, like, statics. Hell yeah. Got to switch batteries in a second. So yeah, so this force has to be 15,000. Cool, or something like that. So let's check it out. So S3, this negative means that it's in compression. And so this 2 is just, square root of 2 is about 1.5. 1.5 times 30, I don't even know what that is, but it sounds like 45. Sweet, so we got 45 divided by 15. Sweet, so this is about 3. And then we have 40 divided by 20. You know what I mean, just trying to do mental math, so maybe that's 2. And it's going to be a little bit more than 2, but 5 is close enough. So hell yeah, so we have 5 times L, and what did we say L was? 5,000, so we got 25,000. Hell yeah. So right there we got 5,000 pounds down, 10,000, and we got 25,000 pounds up. Well, so now we even have a discrepancy, you know what I mean? Because, hey, what's this doing? If I have 25,000 pounds up, so let's draw another free body diagram. All right, sweet. So we're just trying to get, like, I mean, you get, the fact that you get a solution, you might as well use it. You know, you might as well. So anyway, so we have the 5,000, we have the 10,000, which is a little bit more. For sure there's a little bit more. But then, and then we got the 25,000. Well, oh, I shouldn't have done that. But okay, so this is the only box in the universe. I got 25,000 pound force on it this way. Hey, it's going to be going that way due to F equals ma, right? Okay, let's say that again. F equals ma. This is the only thing in the universe. I put a force on it. It's made of mass. And so we're going to have an acceleration. Rearrange this equation. Acceleration is force divided by mass. So I want to know an acceleration is basically just the change in velocity in 1 second. And maybe that's, just for starters, that's all I want to know. I want to know, and the value that you're going to get, the number for this, is going to be the change in velocity in 1 second. If this force is in newtons and this mass is in kilograms, these are the units for acceleration. It's meters per second per second. So there's my change in velocity, and there's my change in time of 1 second. All right, we're really going to run out of batteries on this one, but hell yeah. So again, we have this mass, only thing in the universe. I've identified a 25,000 pound force. It's going to move that way, and it's going to have this acceleration or change in velocity based on this equation. This force is 25,000 divided by whatever mass it is. You know what I mean? Let's say the mass is just 1 kilogram. Holy hell, this thing is going to be moving 25,000 meters per second every second. So if it has a velocity of 0 right now, in 1 second it's going to have a velocity of 25,000 meters per second. And that's just the case. Hell yeah, you know what I mean? If, yep. And this is also good because sometimes you can't visualize that. So here, I always try to come up with ways to visualize something. So 25,000 pounds, how could we could do this. We could have a cliff, have a pulley, and then we could have a chunk of mass that's only 1 kilogram. And then on here, I could have a huge chunk of concrete, steel, whatever, like on a pin, ready to pull the pin, and this thing weighs 25,000 newtons, 25,000 newtons, and then 25,000 divided by 10, that's just going to be 2,000. All right, hell yeah, first battery depleted, but for sure, you know what I mean? I think this is very good, just to get because all these problems, you're just you could solve this and then realize, holy hell, I don't even know the size of this, you know what I mean? Maybe you're just thinking it's the size of the paper. You don't even know what 5,000 newtons is. They're just numbers to you. So this kind of puts some perspective on it. So 2,500 kilograms, you know what I mean? Maybe that's 5,000 pounds. That's a car. So this is pretty cool. So this is a scenario where I'm hanging a car off of a cliff on a pulley, and then I have a rope attached to maybe a steel wire attached to 1 kilogram. Well, guess what? If I pull this pin, the force on this 1 kilogram is going to be 25,000 newtons. I have to check myself before I wreck myself. All right, hell yeah, hell yeah. No, this is cool because one of my favorite problems is the ball chain fountain, where yeah, Steve Mold, man. I don't know. I'll just say that. But hell yeah, just because, I don't know, some people don't come up with simple, arguments for things, and they blow it out of proportion. But in this, I think I'm right on this. I do hey, asterisks on the page, I might be wrong. But you're not going to have continuity on this. This thing is going to have 25,000 newtons on this 1 kilogram. And the second you pull this pin, this thing's going to be launched, because there's no way you're going to be in equilibrium. This thing's just going to be falling, its velocity is 0. this velocity is 0. 1 second later, this thing is just in free fall. And we're basically saying this 1 kilogram is small enough, like you would have to add it to this. This thing is going to be less than free fall. But we're saying that this thing is way more massive than this 1 kilogram thing is pulling. So put that aside. So when I pull this pin, this thing is just going to be in free fall. In 1 second, it's going to have a velocity of 10 because gravity is 10 meters per second per second. Get used to 10 just because it makes your, don't do 9.8 unless you're, I don't know, trying to get 3 significant digits in the back of a book. But anyway, because then you can do a lot more problems just without calculators and just kind of intuitively. Yeah, so in 1 second, this thing is going to be going 10 meters per second. But guess what? What we were saying is that with a tension of 25,000, wherever I wrote it, you're going to have an acceleration of 25,000 meters per second. And that's what we're going to get. The force on this is going to be 25,000 newtons. It's 1 kilogram. F equals ma, says that we have 25,000 newtons is equal to 1 kilogram times acceleration. And the definition of 1 newton is 1 kilogram times 1 meter per second, or 1 meter per second squared. So when we do this, we get 1 newton. And if I have 25,000 newtons and 1 kilogram, this equation has to be balanced. I must have 25,000 meters per second. I just think that's shocking. You know what I mean? I just, just in that, I don't even know what we're doing anymore. But we were just pointing out, oh yeah, just doing free body diagrams. I think it's useful to, pretend like this thing's in outer space, figure out one force on it, and then just imagine it traveling across the universe. We know it's a statics problem, but it's kind of, I like this method of like, hey, like cut out whatever's in your problem. You can cut out anything you want. You can just cut out that little thing. And, but we're cutting out in the box. Alright, hell yeah. And then we just found a force that was 25,000. And if we're saying this is very lightweight, 1 kilogram, I mean, it would be, and then that's what I did. I just came up with a scenario where you could put 25,000 newtons on a 1 kilogram, and you could run this scenario. You know what I mean? You could experience this yourself. I wouldn't be anywhere near pulling this because this thing's going to be flying that way. Very fast. I think 25,000 meters per second after 1 second is very fast. You're going to lose continuity right away, so if you can get this thing to have a force for a full second, hell yeah, it'll be going real fast. You might not be able to get a force for a full second because it's going to be shot out like a gun. But anyway, alright, so we have this idea that we can draw a free body diagram by taking that box, putting it in outer space, finding one force on it, and then just visualizing it traveling in that direction. Going back to our problem and then being like, whoa, this thing's not moving. So we must have to have these forces in the other direction. Okay, hell yeah. So now we're back on point. We have 15,000. We got a 10 and a 5 going this way. We have 25 going that way, so we're 10,000 short. So we must have to have another force this way of 10,000. And so that would mean that this thing is in compression. If this thing was in tension, pulling that way, hey, we would have just more tension upward. And right now I'm just worried about, I'm almost saying this S1 is just this direction. I'm basically saying this S2 is maybe, just this. We're getting rid of the angles, kind of simplifying it. Same thing as I just got rid of that, and we're just saying it's 5,000. But hell yeah, so this is kind of the intro to at least identifying what statics is. But I swear, because this is a complicated problem, I don't think students are going to go back to the basics and being like, oh yeah, no duh, like this is just a chunk of mass, and I can identify at least one force, 5,000 this way. We have leverage. That's where we got this 10,000. So we got 15,000 pounds this way. We have to have at least 15,000 pounds this way. I guess to get this number, I just went right to the solution. And so, hell yeah. So now we have to have another 10,000 pounds to balance this. And so let's see. Let's say this S1. Now, obviously, this S1's going at an angle. So, but anyway, let's try to get a number on this. So square root of 5, that's like 2. And then, we got to do this. So this is 1.5 times 9. Oh, I really don't know what that is. Well, how about, that's about 15. Sweet. Plus 8. I'm just going to call that 20. So we have 2 times 20, that's 40, divided by 20. Alright, so yeah, so we got about 2. So yeah, we got about 10,000. 2 times 5,000, 10,000. So hell yeah. So I think that's also a good strategy, just to look at something like this and just don't give a care about being super accurate. But we know that square root of 5 is close to square root of 4, that's 2. You know what I mean? Square root of 2, 1.5. 1.5 times 10, that's how I did that, is 15. 15 plus 8, I don't know, then I just did 20. I didn't want to go to 25. And then I said 20 divided by, no, what did I do? Yeah, no, 20 times 2 is 40. 40 divided by 16, close enough to 40 divided by 20, that's going to be 2. 2 times L, and hell yeah, we get that 10,000. So now we have, we at least know that, let's say someone did these wrong. Like, let's say these were just, you know, like I would do that. If I wrote my own problem and then gave you the solution, 9 out of 10, these are going to be wrong anyway. Alright, so hell yeah. So I think we're thoroughly done with the intro of what's going on in kind of like this direction and this direction. We simplified it. Now we should probably talk about, you know, the fact... so here's the other basic thing you can do with statics. With statics problems, you can be like, okay, so I have this 5,000 force down. I'm going to have 3,000. I'm going to have another 5,000 this way. So we already did that in components. So I'm going to have a 3,000 that way. Now I'm going to have 8,000 and 3,000. Cool. I guess the other thing that we can do is like, hey, look at this. This is at a 45, let's say. Well, let's just, this has got to have a component up and over in equal amounts. So just keep that in mind. And let's say this is like a 30-degree triangle. And it's not. It's actually this is about a 35. If this is 1 and this is 2, then this is going to be more than 30. Because if this was a half and this was 2, if this was like a half, if this was like a half and this was 1, like if this was 5,000 and this was, the hypotenuse was 1,000, then this would be a 30 degree and this would be 800. But yeah, so this is going to be a little bit more than 35 degrees. And, this is, it's so interesting how, like, I guess what I'm trying to do is say that this component is going to be twice this component. So it's already spelled out for me. Like right here I said, hell yeah, these components are going to be the same. And yeah, because we have this component's 2,000 and this component's 2,000. I'm gonna slow down on this because sometimes even students can miss out on this basics. Is again, we have a hypotenuse. Usually you have like a force in here. It's either compression or tension. That's your bigger number. And you want to know what its components are in like the x direction and then the y direction. And just know that you can do a parallelogram. If I have, what is this? This is going to be in tension, so I'm going to have an arrow this way. Starting from the tail going to the tip, I can either go this way, down and then over, or I can go over and then down. Now this 2,000 has nothing to do with the magnitude of this tension. Let's say this tension is T and it's in some sort of newtons. But these dimensions give you the percentages. They help you get the percentages in both of these directions. So this is cool because I'm gonna take this triangle. So we have the hypotenuse and then we have 2,000 and 2,000. Now these are in millimeters. But now we can figure out what this hypotenuse is. So I'm going to say this is just the larger number. Pythagorean's theorem, 2,000 squared plus 2,000 squared, square root. And what would that be? if this was just, I don't even know. Well, no, we can figure this out. That's the other thing. We're just trying to be in guessing mode. I really should turn off the calculator. We just said that this value is going to be like 1.5. And this is kind of my strategy. Is like if you have components of a triangle, and you have a 45-degree triangle, these two are going to be the same, and your hypotenuse is going to be about 1.5. It's going to be 1.4. So if you guess 1.5, that's going to be an overestimate. But you know this hypotenuse can't be more than 1.5 2000. So that's going to be 3000. So you know that this hypotenuse, and we're not saying the tension right now. That's kind of the confusion. We'll get to it in a second. But we're just saying the direction of this is going to be kind of in this direction. It's pointing from here to this point, and I can measure this on the wall to be 2000. I can measure this distance across to be 2000. And so just this distance from there to there is what we're doing. You call it D, or just the larger numbers of the hypotenuse, is going to be about 3000 millimeters. Cool. So now what do we do with this? Well, we say that this component, what I always say is that this component is a percentage of the hypotenuse. And that's where we get into, let's say this is a 45-degree angle. It gets into what I like to say is sines and cosines. If we have sine of an angle or cosine of an angle, that's just the percent of the hypotenuse. You know what I mean? That's just the percent of that larger number. So right here, let's say you, like, everyone should know that sine of 45 is 0.707. To 3 decimals, it's really accurate. Sine of 45 is 0.7071. So you can just, who cares about the 1? This is really accurate. I like to think 007, whatever. Or you just 0.7 and call it good. But 70% of the hypotenuse. That's what that's saying. So if my hypotenuse is 3000, I take 70% of it. Now, let's say you don't know what 70% of 3000 is. I call this the restaurant method. Just do 0.1 or 10%. Oh, hell yeah, 10%, that's going to be 300. And then multiply by 7. All right, that's going to be 2100. So if I really do have a hypotenuse of 3000, this side is going to be 2100. And we're kind of right in that ballpark. Cool. All right, so there you go. And then if we said our hypotenuse was 3000 and one of the sides is 2000, then you could say 2000 divided by 3000 is going to be like 0.6. Repeat. And this is going to be 66.6% of the hypotenuse of that larger number. And so I like to think of sines and cosines as percentages. I like to think of these components in this direction and this direction as percentages of the hypotenuse. I think the human brain really enjoys percentages way more than fractions of a whole, but that's what we're getting at. Sines and cosines are fractions of a whole between 0 and 1, like 0.5, 0.866. But these are also percentages of the hypotenuse, 50%, 86.6%. All right, hell yeah. So this is fun because all we're doing is like, hey, so can I take this problem and then just kind of mentally, we were using these, so we did it. We used these dimensions or maybe we didn't. Actually, maybe we didn't. All we know is that whatever this dimension is going to be twice. That's all we know on this one. And then on this one, we know that these dimensions are going to be equal. Wait, is there one more thing that we can gain from this? Or is that it? No, hell yeah. No, there's for sure one more thing to gain. Okay, so this dimension is 0.7 of the hypotenuse. And if we did a more accurate, you know, I got 0.66. Hey, that could round up to 0.7. But let's do this more accurate because we know it's not 2,000 times 1.5. It's 2,000 times 1.4142. It's 2,000 times the square root of 2. That's going to be this dimension. So let's take square root of 2 times 2,000. And hell yeah, so this is going to be, this hypotenuse is going to be 2,828. So then if we take 2,000 divided by 2,828, we're dividing by a smaller number, this is going to increase. So we have 2,000, I'm going to store that as x, 2,000 divided by x. Hell yeah, 0.707. Okay, same thing here, we're going to find the hypotenuse. So we're going to have 1,000 squared plus 2,000 squared, just, you know, Pythagorean's theorem, this squared plus this squared, square root that. Hell yeah, so that's our hypotenuse. And then I'm going to store that as x. So now we're going to have 1,000 divided by that hypotenuse. So this is going to be 44.7% in this direction. And then this one is going to be 2,000 divided by x. So we have 89%. And the visual way to do this, and this is why I'm kind of going, like I said, I'm going over this more for me because it's just like, yeah, what's the fastest way? Take your hypotenuse. I always like to divvy it up by 2 and be like, oh yeah, hell yeah, those look about the same. You know what I mean? And you could maybe see that this is a little bit smaller. Not really. It's about 50%, so that's what we're going to say. Like, obviously, this dimension is 50% of whatever hypotenuse. And it's the hypotenuse is what you're after. Look at this. Like, this is the equation for the compression or tension, whatever. That is the magnitude of that tension or compression. And so half of it's going to be, you know, in the up or down direction. Now, basically, so then the other thing, even if, like, this could be like a 35-degree triangle, but even up to 35, like, this is substantial, and it's almost 100%. I think this angle is less than 35. Isn't that what that means? Inverse tangent of 1,000 divided by 2,000. Sometimes it's hard to know what side of guesstimating you're on. Yeah, this is a 26.56 degree. I almost feel like they didn't draw it to scale. Like, does this look like twice that? No. This looks a little bit taller. Alright, hell yeah. But yeah, so if your angle's less than 30 degrees, oh, this just approaches 100. So that's what we're going to say for this. Forget 90. We're going to say whatever this vector is, we have 100% of it that way, and then 50% of it up and down. And I should say it's either this way or this way. This dimension. And what is this? This is in compression, so it's pushing back on this thing. Alright, so let's do a new free body diagram. And let's put all these on here. So we're going to draw our box. We have 3,000 this way. We have 8,000 this way. Cool. We have this value up. Are we going to call it 25,000? I guess so. And then over here, we're going to have this. We said it was 15,000. But it's going to be two components at 70%. So 15 times 0.7. Yeah, maybe it's 10,000. So we're going to have 10,000 that way and 10,000 that way. And like I said, we're still just kind of guesstimating. Now this one's going to be 100% that way and then 50% down. And this one's in compression, eh? Yeah, because we're trying to balance that. Yeah, no duh. So right here with real values, we have 18,000 down, 25,000 up. So 25 minus 18. And then we should have 7,000 down. Sweet. So there you go. We have 25 down matched with 25 up. Cool. So we have 13,000 this way. And then, so that's going to be 13,000 this way. 13,000. And then let's see if we did it right, because this should be a half of what this is. Yeah, 13 divided by 2 is about 7. Hell yeah. And so there you go. Like we have a general picture of probably what's going on here. And it's nice that we just kind of, I mean, you could have got just actual values. But I'm just using these as a guesstimate. I really don't care about 100% actual values. I think it's just good to be like, well, like, because that was my first question. Is like, you got 5,000 pounds. Is any member of this thing going to be more than 5,000? That's kind of a decent question to ask. You know, it's like the whole question of like, hey, can I don't know, can like a weightlifter lift more than their weight? By pulling down, you know, if they're just standing on the ground? Hell no. You know what I mean? Just overhead pull. You for sure, draw a stick figure, you for sure can't pull down more than your weight. You're going to pop off the ground. Now, if you're glued to the ground, you got like hooks under your feet, hell yeah, sky's the limit. But no, you can't pull more than your weight. So there's just some problems, like this is kind of what you're visualizing. But we already went over like, hey, the leverage. Yeah, so you have 5,000 newtons down. But yeah, we're seeing that you have, I mean, even due to this being fixed to the ground, you get that extra more. And did I even do that right? If you have 5,000, what's 5,000 times 0.7? 5,000 times 0.7? Yeah, 5,000 and 3,000. That's what we were shooting for. So, yeah, so 8,000 down. And then, yeah, you get quite a few numbers that are bigger than that initial 5,000 newtons. Cool. All right, hell yeah. So now I think, I don't know, you know what I mean? That was kind of the basics. And now we should probably start to dive in and get just a little bit more nitty gritty. Yeah, and I'm going to take about 10 minutes to see. I mean, yeah, that's the only thing. I'm going to. Yep, I'm just going to take about 10 minutes. Alright, hell yeah. So we're back, and yeah, I took a little break, and what I was going to do is I was actually going to, you know, put this on grid paper, because there's one thing about statics problems that we're going to go over, we're going to talk about. It's that, and let's talk about it right now, but it's line of action of a force. So let's say, I think it's just easier just to say like these are all in tension. But if I pull on this point right here down, let's say, it's no different than attaching the string. Let's say I have a string right here. It's no different than attaching the string right there. And so, sweet. So let's talk about that for a second. So if I have this rectangle, and now let's say I have a string, and then I kind of like glue it, like maybe make a groove and then glue it all the way into this thing. So there's no difference between the string pulling on this point, like a point right here, a point right there, a point right there. And we could say that's the same thing as having like a little, maybe like a little dowel. So from a three-dimensional perspective, maybe we just have a little dowel sticking up. And then the string is going to be attached to the dowel and it's going to pull it. So if we pull from right there, that's the same thing as having a little like dowel sticking up right there. At any point along here, we're going to be pulling. The same thing with pushing. So if I have this and then I, you know, take a rigid, you know, object and then push kind of on that point, it's no different than pushing right there, pushing right there, pushing right there. So that's kind of the general idea of line of action of a force. And so what I did was I just said, hey, I know that this force is going to be in this direction. And it also brings up the idea, as long as these are pivots, these members can only see a tension or a compression, and it has to be in this direction. And that's part of the idea of a two-force member. I don't know, just kind of visually, I'm okay with that. I see it. I don't, yeah, I should take about a 5-minute break and then explain what a two-force member is, but maybe we'll do that later. But yeah, for what we know is that the force is going to be right in line with this one, and that one. Cool. And, but let's take a step back. Where we're going with this is like, hey, if these two lines meet right there, well, now we know that, yes, let's talk about that. It's like taking this rigid body, and then let's just pretend that it has a chunk up here. You know what I mean? Just kind of an invisible chunk. And we're going to have our invisible little piece of dowel that we can put a string to. And maybe we pull down from this point here, and then we pull. So we're going to be pulling this way and pulling this way. Thinking of things in tension is way less complicated than thinking things in compression. But yeah, I have this imaginary little nubbin. And because I'm pulling from this nubbin from two different places, this kind of gets back to the basics of statics. So this is kind of like the first problem that you do, is you can take these two forces, and you can say, well, that's going to be the same as just, adding these vectors together. So if I'm going this way and then straight down, I'm going to go this. I'm going to add this one to this one. There you go. Or I'm going to add this one to that one. And that's the parallelogram method of adding vectors. If this is A and B, this is A plus B, and this is B plus A. Hell yeah. And then this is going to be the resultant vector. So there you go. So if these were my two vectors, then I would just have, hell yeah, I would just have this way and then that way, so we would have a resultant somewhere in between there. So I can say, booyah, there's my resultant from that point. And this is going to be useful because with statics, you only get so many unknowns and so many equations. So let's talk about that part from an intuitive perspective. Alright, booyah. So now we're going to have to go back and draw just our kind of our free body diagram. Going to have the box. Now we're going to, we kind of put values on these, 8,000, 3,000, 25,000, 10 and 10. These are going to be the same, and then this is going to be twice that. Okay, but now we don't know these. Like, we got these from the solution, but now we're going to go from the perspective, like, we don't know those, but we still know they have components. So we know that we're going to have, we do know this load is going to be 8,000 down and 3,000 over. Cool. We know that this one is going to be up. We just don't know. We don't know that one. This one just has one component up. This is going to have two components, and they're going to be equal. Now, we don't know the direction of these, but we did, yeah, we thought we did, from there. So we think this one's for sure going that way, so let's draw that in. And then we thought this one was going that way. So these are going to be equal. And now we have this one that has a component, and from our original drawing, we kind of figured out what direction these have to be. Not really. I mean, we went off the solution and then got the values for these. It would be interesting to go back and to see if we could have intuited these values without the solution right here. But we said that this one is going to be double whatever. So if that's 2 compared to this one, it's going to be that. That's going to be the case there. All right, so here's what our diagram looks like. And we only have we don't know any of these. And then so our equations, and this is 1, 2, and 3. So this is going to be, in the down direction, like this is vector 1, this is vector 2, and this is vector 3. So using kind of the free body diagram in Newton's laws, it's like, hey, we have this triangle. Let's say we just identify one force on it. Well, that means that it's going to be moving this way. but then we go back to our setup, or whatever you call this, our project, and we see that it's not moving. And so we know that in this direction there has to be a force that's equal and opposite. Okay, so that's how we get these equations. So then we say that in this direction we have an 8,000 down, and that has to be balanced by this one up and then these two down. But we don't know any of these three. Okay, so that's one equation, and we don't know, we have three unknowns. You know what I mean? So this is kind of a good way just to like visualize the problem. Because I think what happens is that you get equations and then you just run into the trap of just being like, okay, I'm going to get one equation that's 8,000 plus this one minus this one, or like minus 8,000 plus this minus that. And then you do that, you put that on a page. And then we're going to do the same thing in the y direction. So now we're going to say, hey, let's say I have a force over here that I've identified. And here I have this 3,000 force that way. So I've identified a 3,000 force that way. But we know from our project this thing's not moving that way. So I must have to have a 3,000 pound force that balances. And that's where we get into, so back to here. So we have a negative 3,000 minus this one plus this one, has to balance out. So these two going this way has to equal this one going that way. So we have another equation. Two equations, but we still have hella unknowns. You know what I mean? That's two more unknowns. You know what I mean? Because the ones in this direction were these three. We didn't know these three, and we had one equation. Now we have another equation, and we don't know these two. So that's going to be two equations, 5 unknowns. So that's where using, and I don't know how hard this one's going to be, but that's where the idea of line of action can be useful. Yeah, so let's talk about this. So I was thinking that we would take this one up to here, and then this one up to here, and then take it right from there. But then what we'll do is we're going to add these two vectors together. Oh, yeah. Never mind. But now the third equation for statics is that nothing is rotating. So I think it is very useful. And especially just get a fresh sheet of paper. You know what I mean? A true free body diagram is cutting away all supports. Cutting away the chunk of mass you're interested in. And then knowing it is mass, that's very important too. Even though they say the mass is negligible on this, well, I don't know. I think it still is important to identify that it is a chunk of mass. We are going to have forces on it. If those forces aren't balanced, this thing is going to be flying across the universe with a change in velocity due to those equations F equals ma. The other equation, that it could be spinning. So if giving a chunk of mass, if we have a center of mass right there, and then I just put a force this way. Cool, I could balance it with a force this way. These could be the same, but then from this setup, this thing is going to be spinning. The only way for this thing not to be spinning is to put the forces directly opposed each other. I guess the forces could be directly opposed anywhere. They could be over here. You could have a force this way and a force down, and it's not going to spin. But if you put the forces right in the middle, hell yeah, it's not going to spin. But yeah, you could have a force in the middle and then a force off to the side. And it's going to spin. You could just have this chunk and then just one force that's just off to the side of the center of the mass. Then it's going to do two things. It's going to travel across the universe this way, and it's also going to spin. But I was just trying to break it down to a scenario where, you know what I mean, you have, let's say you have a force right here, but then you have a force over here. These are going to be equal and opposite. So then you know that at least the center of mass isn't going to be traveling in this direction at all. But it is going to be spinning because you have this, because the forces are kind of lopsided, and you have a net torque on here. So whatever distance this is, you have FD, that's going to be your torque, and the equation for motion is going to be, the sum of the torques is going to be I alpha, the angular acceleration. And I is the second moment of mass. Alright, hell yeah. So from that, let's see how much torque we would actually generate. So if I'm going to have a force here, here's the center, and then I have a force here. Well, hell yeah. This distance right here is going to be, so let's say let's say this is the point O. How much torque am I generating? Well, this force, from this point is going through this point, so it's not, you're not generating any torque from this. You know what I mean? I guess it would be the equivalent of having a door, having hinges. This setup right here is like, hey, I'm going to push on these hinges this way with a force. And then I'm also going to push on the door this way with a force. And this is blowing my mind right now because I never really thought of this. This is exactly what's happening when you open a door. If the door was a free body diagram that I'm, the way that I teach it, just floating in outer space, and you go push right there on this door, sure, maybe it's got a center of mass, well, I mean, like, who cares even where the center of mass is? If it's not attached to anything, this thing's going to be going across the universe that way, due to that force. Now, it's not going to be the full magnitude of the force going in that direction, because some of this force, some of the amount of this force is going to be turning this thing probably that way, because you're going to have a center of mass of this door, because you have a distance away, you generated a torque too. And if this is the only force applied, and that force is making rotational motion and translational motion, this force can only be equal to, you can't just say like this is not equivalent to having a force on the center of mass of the door, having it go across the universe with a change in velocity per second. That's where F equals ma. This door has a mass. There you go. And you're putting a force on it. You're going to get some sort of value for acceleration. And again, that value for acceleration is force divided by mass. Hell yeah. If you know the force and you know the mass of the door, you're going to get a number for the acceleration that's going to be change in velocity per, 1 second. That's going to be the value. Every second is going to be increasing in the change in velocity. I guess, quickly, the take-home point here is that you don't have a force that goes through the center of mass and it's lopsided. Well, it doesn't mean that it's still going to be going with this magnitude. It's going to be going with a little bit less because now it's also rotating. And that's the deal with whatever force that you're using. It can only make the molecules of this door have a overall velocity or kinetic energy of, basically this number, this change in velocity per whatever mass is going that velocity. And just for things that rotate, that's where it gets like, hey, if this thing is rotating about maybe the center here, like these molecules don't have any extra velocity due to that rotation, but hell yeah, the molecules out here that are rotating this way and rotating that way are hella moving, and they're just spinning, and then, so that's, you can add those together. So these molecules that have velocity due to some sort of rotation, Anyway, so hopefully that makes sense, is that, yeah, if you only have this constant force, some number, it can only change the velocity of mass, proportional to this number. And so it can either be all translational, it could be all rotational, but if it's a combination of both, you can't have the same magnitude of translational and rotational. You can't just get extra change in velocity, because you have little chunks of mass that are experiencing a change in velocity. So all in all, you can only have, the same amount of mass changing velocity per second from this value of the force. All right, holy hell. That was probably not worth it. But what do we got? So we have the idea of torque. And yeah, it's just kind of wild that, yeah, if you put a force on a door, yeah, the hinges have to push back, else this door is going to be traveling that way across the universe. But when you go to push open a door, it doesn't. It doesn't go across the universe like that. It just kind of rotates on the hinges. So the hinges must have the same force going in the opposite direction. Cool, but you are generating a torque from those hinges. So now you have that distance away, you got this force. Alright, hell yeah. And some of these fundamentals is just like, I don't know exactly why they work, but we're gonna look at this one, because I'm gonna sum the moment. I'm gonna call this point A, this point B, and maybe this point O in the middle. I'm gonna sum the moments about point A. So if I do that, sum of the moments about point A, what are we gonna get? So we have this force is going through A. It doesn't generate any torque. We have a force over here. So sweet, maybe that's going to go in that direction. So I have, we're going to have the negative direction. We have a force times a distance, FD. All right, so that's the sum of the moments about A. Now let's sum of the moments about B. Cool. I don't even know what we're going to get, but hell yeah. Like I thought, maybe we're going to be this way. So sum of the moments is R cross F. So we're going to be going in the direction towards the force. Now this force is going right through point B. So we're going to be going over there and then sweeping our hands in the direction of that force. Our thumb is going to be the sign. So we have a kind of the negative direction for that torque. And that's going to be, basically... distance could come first, but force times distance, there you go. So we got negative FD. All right, now we're going to sum the moments about this origin. So we're going to have two forces. We're going to have this force, so it's going to be in the negative direction, and then this force, fingers towards the hinges, and then sweeping the fingers in the direction of the force. So that both of those are still going to be down, both of them. And so we're going to add them together. But when we do, this distance isn't the total distance, it's d over 2. So we got force times d over 2 plus force times d over 2. Or it's the force times 1/2 d plus force times 1/2 d. So you still have force times distance. And this, like even in a situation where you do have a net torque and the door opens, we all experience that, at every point along here, you're going to get the same torque. So it brings up this principle in statics that if this thing is not moving, because like right in this scenario, it looks like we would have a net torque, but what happens is like maybe you have two other forces this way and this way. I don't even know if I actually drew them right, but if these are a positive, they would have to be opposite. So we would have forces this way and this way. So these two forces would make this thing rotate in the positive direction, or the counterclockwise direction. These two forces, even if we just had one on here, yeah. So let's go over this because it's kind of the basics, but it's important. Alright, so we have just maybe a force right there, a force right there. These are going to be, and the way I drew them was negative. So now we have to have positive forces. I'm going to have a force right here, and a force right there. Now let's say I just had these three. Cool. So this force and this force are making a clockwise rotation. This force over here is going to be counterclockwise. So this could balance that. But now what we run into is that we have, these two forces are in the up and down direction, and they can cancel. Now this thing's not going to be maybe moving this direction at all. But because we have this force that's going to stop the rotation, now we do have a net force this way, so we have to have something to balance it this way. So there you go. So we have these two forces are going to be positive rotation. These are going to be negative rotation. Those are going to balance. These two forces in the vertical direction balance. These two forces in the horizontal direction balance. All right, hell yeah. And it just brings up the point that if I take the sum of the moments from this point, this force isn't going to be in there, but I'm going to have a positive F. Let's say this is D, and this is going to be A. And we're going to call this force S and this force S. I should have called it P, but whatever. Yeah, from this point, call it A. So the sum of the moments about A is going to be F times D. So we have a negative F times D. Then we have, how about this one? We have a positive F times 1/2 D. Sweet. And then over here we'll have a S times A. So we have a positive plus S times A, positive S times A. Sweet. So it looks like we have negative 1/2 FD plus S times A. That's going to be the sum of the moments about A. But why not take the sum of the moments where two of these forces come together? I could do it right there, where this one and this one come together, or just right over here. Yeah, but let's do it at this point right here. So if I sum the moments about this point, I'm going to have this one and this one are the only forces that generate a moment. So I'm going to have F times D. That's going to be in the negative direction, and then I'm going to have plus S times A. I'm sorry. This distance is going to be D divided by 2. I was like, yeah, so we got F times D divided by 2 plus S times A. So we get the same value as we did. All right, and now with more complicated problems, let's throw in another force P right here. And this is what will happen. If I throw a P right here, we have a line of action. I could put the P right here as well. It doesn't really matter, but we'll leave it right here. And if I sum the forces, just around any point that's not in this line of action, I have to include it in the moment. You know what I mean? So if it's at a 45-degree angle, it's going to have an upward component and an over component. And but if I just sum the moments about point A, point P goes through A, and so then I'm going to get these, basically this equation again. And this equation with the sum of the moments doesn't include P. You know what I mean? So there you go. So I found a point where one of the forces, when it comes to summing the moments, is irrelevant because that force goes through the point where I'm summing the moments. So that's going to be critical for problems where, hey, maybe you got too many unknowns. All right, so now I think it's important to go back and look at this problem and being like, well, why? Let's get rid of this one. If we get rid of that member, why can we solve this easily? Well, we're going to have two components in this direction. So, and let's try to do them right. So if we get rid of this component, I'm going to have a force down and a force over. But basically, I'm just going to have a force in this direction. Cool. So if I have a force in this direction, this one's probably going to be in tension, and this is going to be in compression. Like if this one wasn't in compression and it was just a rope, then this thing would just crash into the wall. So that's another way to be like, well, does this one have to be in compression? Well, yeah, just turn it into a rope. And visually, I think you're like, whoa, 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 yeah, we can't turn that into a rope. But over here, you're like, well, could I turn this one into a rope? Sure. When can this one not be turned into a rope? Let's say, let's say this one's a rope and this one's a rope, and we're just holding it, and then we're like, well, what? Like, can we just bring it up here? No, this rope's going to collapse. You know what I mean? And then let's hold it back into the original position, and if they're both ropes, can I, like, swing this down? Well, yeah, this one's going to be in tension, and this one's good, but this one will collapse. So depending on if we have this and we're, like, you know, pushing it up or down, you know, if we're applying enough tension this way, then one of these has to be a rope and one of these has to be compression. Now if we take this and we just move it inward, like if we just have a force that pushes that way, well then they both have to be in compression. That's another useful thing to look at. But in our situation, and I'm still going to analyze where we just don't have this one and we're just kind of pulling straight down. Well, no, we're pulling at this angle. So we're trying to do this with it. Then I think as long as this, yeah, this is fascinating me because I would want to do a separate video. But I think as long as this this component. Alright, so as long as this component of this force isn't on this side, like it's like straight down at a perpendicular or this way, then this one will maintain tension. But I think you get to a situation where if we actually push on this way, minus this, yeah, they're both going to, you know, need to be compression members. Cool. Alright, that said, let's see why. So that's where it's just like, it's probably easier just to be like, hey, let's just take a straight down 5,000 and then figure out, and let's do that. Let's just say we have 5,000 newtons straight down and we don't have this member. Like, how hard is this problem to solve? Well, we don't know this component. And then let's figure out, well, what did we need? This one's going to be in tension. So this one's going to have a component this way and a component this way. So if I'm not doing the actual hypotenuse, I like to do an open arrow just to know that these two arrows are probably, you know what I mean? So then I can actually put the actual vector in and just do like a solid arrow. Now this one's going to be in compression, so we have a solid arrow here. And now to get there, we can either go this way and then that way. Cool. And, or, you know, so a lot of different ways to do this, but I could also go this way and that way. So this is showing the parallelogram method. I typically don't put too many arrows on the page, just whatever makes sense. Sometimes this is easier to visualize, where you have your main hypotenuse and you have your components going from here. Or, you know, sometimes it is kind of nice to be like, okay, here's my main vector, and I'm going to go this way and then that way. Cool. Alright, so let's do an overview of this and see how many equations we would have. So we know that this 5,000 straight down has to be balanced by this one and this one. So there you go. We have one equation and two unknowns, this and this. Cool. So now the second equation is going to be like, hey, we don't have any force in the y. So this vector and this vector have to be equal to each other. All right, sweet. Okay, so now we have another equation, and we had 2 more unknowns. So that's going to be, so this is 4 unknowns, but we have 2 equations. Yeah, and I haven't done these statics problems in a long time, but all the way through. But then it's just like, well, we only have one more equation. We have that moment equation that it's not spinning. So then we have to pick a point where maybe the forces go through that point, and then we know this force. So what we're going to do is like choose this point right here. Like this component and that component goes through point B, and also, oh damn it. So this is where this one does get trickier. Let's say I like because if I take the moments from this point, no, never mind. I don't know what the hell I'm thinking, but no, this is a very simple one where you would just take the moments from here. These two, and then the way I have it drawn, it looks like this one is going through that point. Well, that's not true. You know what I mean? I can say that this vector goes through that point and this vector goes through that point, even if I draw it like that. Just because I can draw this vector this way with the solid, and I could say it goes this way. These are the components of that. So yeah, this is probably the better way to do it. Start at the point where the force is working, draw your kind of your hypotenuse, your vector in that direction, and then draw the components from that tail. Cool. Because now we're going to sum the moments about this point. This one, and this one go through that point B. This component doesn't. So then we have a simple moment equation that says, hey, 5,000 times 5,000, so it's like this force times this distance, that's in the negative direction, has to be balanced by this one, which has to be a positive moment. So then we have 5,000 newtons times 5,000 millimeters. That's going to give you 25 hella Newton millimeters of torque. And then that's going to equal whatever this vector is times 2,500. Cool. So yeah, it's going to be double. So this has to be 10,000 newtons. Cool. And so even just right there, that gets us, I mean, that's in the ballpark of what our guesstimates were at the beginning of the video. Of like, hell yeah, we thought this was, 13,000, 7,000, 10,000. So even going back to this is what I like to do for problems. And I don't know, and it's always a bummer because some of these problems, they have like that one trick that if you weren't taught it, then it's like, I don't know how you would find it. But I mean, I'm sure the trick for this one, I haven't solved this one yet, we're just kind of slow rolling it, is the fact that, like right here we got rid of this support, but, we could take our moments from there and, hey, everything canceled except one unknown. So now we're going to see if we can do that, just kind of even from an intuitive perspective. So now this picture is not drawn to scale. But what I'm going to do is I'm going to drive this line up and then this one over. And this might be good just to do these for all these forces that we don't know. Because when I saw this problem, I was just like, oh, maybe they go through that point. You know what I mean? I don't know. I just thought that was, if that force went through that point, maybe that would be useful. Probably not. But anyway, so hell yeah. And it was just kind of fascinating. I didn't know that you could potentially just have an imaginary point and then just pretend that, you make this rigid body go up and around there, just massless but rigid. and then throw a piece of dowel in, and now you have either tension or compression on that. And well, that's where I thought you could, I was wondering if you could do this a different way, just like knowing that these are the vectors going through there, and then doing the parallelogram of like adding these together, but you don't know what direction they are either. So I don't know what the generic would be to get a universal vector adding these when you don't know their magnitudes, because the direction, I mean the magnitude of this is going to change, and whether they're positive or negative, this thing could be the resultant of these two forces coming to that point could be anything. Could point any direction and be any magnitude. So this is going to basically be very useful for when we sum the moments. But then, like back to this one, like let's say we, you know, let's say this for, I don't know, kind of, like when we sum the moments on here, we gotta cancel out these two and that one and this component of this. You know, so we were just left with one component of this. But what we're going to run into is if we sum the moments, let's call this O. If we sum the moments here, yeah, the forces due to compression or tension of those won't be involved in the moment equation. But this thing has two components. Let's see, this one's going to be in compression, so we're going to have a component this way, and then a component this way of this force. Sorry about that. So there you go. Those are components. And if we sum about this point, hey, this component that we don't know is going to have a positive. This is the distance away this component is. And then this component is this distance away, and that's also going to have a, so we're going to generate a positive moment, but we have two components that we don't know. And then so we have this moment equation, but we still have two unknowns. So that doesn't help unless, so I think the trick to this problem, so now we're kind of getting to it, is like, well, don't divvy this up into components. You know what I mean? Let's say we know it's a compressive force. Cool, that compressive force is going to go right through here. So then here will be the trick. Figure out the perpendicular distance to here. And then hell yeah, now we're just set. And now I'm kind of interested, because sometimes finding the perpendicular distance is hard. But didn't we just say that the moment, I mean we're trying to sum the moments about this point. Isn't the sum of the moments about this point just a cross product? So isn't the distance from this point to A, isn't that just a vector like R, you know, RO to A? O has now, you know, coordinates. It has like an X and a Y coordinate. A has an X and a Y coordinate. And then so you have two components. And when we do the cross product, the only component that we're interested in, and see how we get from O to A from a perpendicular perspective. I mean, this is where you want the parallelogram, you know what I mean? If, you know, like, if I know, you know, I drew this perpendicular. Yeah, so the only effective way to get to A, oh, is this going to work, or am I just saying wrong stuff? Because I would probably have to have my coordinate system this way. Is that what I'm saying? But yeah, forget all that. But yeah, if I want to go from O to A, I'm going to go this way, and then this way. And when, let's see. Oh yeah. And this force, you know, basically the line, it acts at this corner, but again, you know, and that's where compression forces are a little bit trickier, because you're just like, well, is it the same thing as pushing on this corner as like pushing on a piece of dowel right there? And isn't that the same thing of coming in right here and then applying this S1 right there? Hell yeah. So it's the same thing as just putting that S1 right there. And then so, yep, so this is the distance away from O that's generating that moment. And yeah, I did throw myself for a loop because I wouldn't know what this tilted coordinate system is. And I don't even know if I'd want to do that. That's a good skill to have, to be like, hey, can I tilt this coordinate system? Because if I did do the cross, if I just said this was x, this was positive x, this was positive y, then I could, and let's just say this is, for all purposes, this is the origin. And so this point, well, I already said this was the origin. Okay, so this point is going to be negative, negative. So let's say it's just negative 10, negative 8. Cool. So we just threw a couple values onto there. And then this is in negative 8j hat, negative 10I hat. So we go negative 8 in the y direction, negative 10 in the x direction. Cool. And then we have a force, this S1, we're just going to call it 5. Cool. We have 5 newtons. And these are going to be in meters, 8 meters, 10 meters. Cool, so now let's see how the cross product works. We know that the moment is just going to be this force times the distance. That's going to be 5 times 8. We'd have a 40 Newton force. But let's see how the cross product works out. So the moment is going to be R cross F. And you do the R first. So we're going to have, and the R, how to get from O to A is we got to go negative 8j, negative 10I. So this R is going to be negative 8j. Well, I should do the I first. So it's going to be negative 10I minus 8j. That's the R, and we're going to cross it with the force. The force is just all in this I direction, positive I. So we're going to do 5I. Cool, and when we do this cross product, I like to do the cross product this way. You could do it, this is good. 2 ways never to mess up the cross product. Draw your x, y, and then take your fingers in x and then sweep them into y. So then you have your z coordinate coming out of the page. That's how you do a proper x, y, z. Don't do z the opposite way. Always take your fingers in x, sweep it into y, and then your thumb's going to come out of the page. Okay, hell yeah. And then and then probably do another one right next to it. That's I hat, j hat, k hat, just so you're not like overlapping. But now you're set to go. If you want to cross anything, you just put your fingers in I, sweep them into j. So I cross j is positive k. Let's go j cross k. That's going to be j cross k is positive I. And then let's go k cross I. Hell yeah, that's positive j. And I would do it in that order. I would go ijk, and then ijk. If you write this on your page, you can't mess up the cross product. Because if I go in this order, I'm always going to get a positive. I cross j is positive k. J cross k is positive I. I cross j is positive k. Cool. And if you went the opposite, k cross j is negative I. Let's try that one. K cross j, hell yeah, my thumb is in the negative I. Now how about j cross I? J cross I, hell yeah, my thumb is in the negative k. And then I cross k. So we have I, and then sweeping it back into k. So you kind of have to tweak your wrist, but there you go. We got a negative j on that one. All right, so from that, that's the fundamentals there. And then, so I would at least draw, I do this. Anytime I'm doing cross product, I might just write this, ijk, ijk. But then if you're not quite sure where this comes from, hell yeah, do a proper x, y, z coordinate system. Sweep your fingers, sorry. And I shouldn't just repeat myself. We're done with that. But yeah, fingers in x, sweep them into y. Z is going to be in the positive direction. Cool. And let's do it. So we have this, we're going to have negative 10. And we're going to do 10. And then you can't mess up. I mean, you're going to multiply this times that. Multiply this times that. I mean, if you're... And then the other thing is, if you cross... Like if I'm in I, how do I cross I into I? I can't move anywhere. So then that's just 0. You know what I mean? The whole idea of a cross product is like a door. where you have a force times a distance, and that's going to give you leverage. So a cross product is a vector, and the vector means something. The vector doesn't mean, you know what I mean, if you have a force and a distance and you're crossing those, you get a multiplication of those two, which is a useful quantitative thing. Yeah, force times distance is what we consider leverage. And if this is a perpendicular degree angle, hell yeah, we got to use all that force. But the second this isn't, let's say it's coming out like at a 30-degree angle, you know what I mean, we only get to use half the force in the actual direction we're using. The other component goes away. And so that's what we're going to see here. So if I have a negative 10i cross 5i, that is 0. You know what I mean? And you could write it out. You could do negative 10, positive 5, I cross I is 0. So if you wanted to write it out, but I probably wouldn't. I would just know that you can't cross I, but you can. It's going to be 0. So I'm going to look for this one. I can say, hey, I can cross j cross I, and that's going to be the only one of interest. So we're going to have negative 8 times 5. J cross I, is that in order? No, because it goes I cross j. So that's in opposite order, so we're going to have a negative 1. I do the negative 1 first. J cross I is k hat. So instead of saying negative k hat, which you might lose the decimal, I just do negative 1 k hat. And now I can easily see the negatives goes away, and I got 40 Newton meters in the k hat direction. Now let's go back to it. We said this was our distance to here. This distance was irrelevant because we could take this force down the line of action and just put it there and then have this as my R value. So if I did that, this is 0, 0, and then this is just negative j. So then I would just have an R value of negative 8j, and this would go away. Yeah, so this part of that distance was irrelevant. It didn't matter if this force was acting way the hell out here. You could still do, you could figure out this distance vector, cross it with this force, and you would still just get that component. Alright, hell yeah. So now we're going to see, it's just like right now I'm just hella confident because I could set this problem up maybe from a graphical perspective. Like let's say I didn't know the trigonometry and I was like, I knew at least to get my sum of the moments from there. Well, as long as I set up the geometry right, and I'm going to do that. You know what I mean? Let's say no one has ever solved this problem like ever. And then you're just like, how would I solve it? Because a lot of the Irodov problems, and I will say a short little story, is I tried an Irodov problem like last week. And I just oversimplified it. And I got the answer right away. I got the wrong answer, and it was like horrendously wrong. And then so I was just like, what am I missing? I couldn't figure out what I was missing. And that was a bummer. But then I just went right for the answer. You know what I mean? And then the answer was just like a super, it was almost like a magic trick. And I was just like, I don't solve problems that way. But if I did the problem the way that I like to solve problems, like kind of from an analytical perspective, I would have got just the fact that you can get the right, like this being the right answer is not helpful. But if you can find a way to like numerically get the right answer, so I'm gonna do this graphically. I'm gonna graphically get the right answer. And that's just going to like really boost my confidence in then going back and working on, you know, like the geometry, you know, of this problem to get these equations. You know what I mean? But I think once you actually get the right answer from a numerical, graphical, you know, just like the non-technical way, it at least gives you a right answer that you can then compare from this technical perspective. But doing something in a technical way, man, you could be off by a little square root of 2, you could be off by a negative, and you'll just lose your mind. And then you're going to turn in some work that's wrong, and you'll go back and then like, I mean, you still can check your work. Like if these are your forces, you can be like, you know, go back to that free body diagram. And if you found all your forces, and they don't add up, and this thing's moving across the universe, hell yeah, you did something wrong. But that can be a mentally deflating too, when where you don't know where your errors are going to be. Okay, so hell yeah, you know what I mean. I don't mind making this 5-hour video. So I'm gonna get some graph paper. Yeah, and we'll do it up, and we'll see how accurate we get. Because, I mean, does that make sense? I'm gonna take my moments from here. This is gonna be my only unknown. Cool. I know these forces, and that's it. And then I can actually find S1. Once I find S1, I should be able to go back. Maybe I have to take moments from another point. I don't know. You know what I mean? You can take moments anywhere. You can have. You know, you only have one, I think, am I saying this right? You only have one equation for forces in the y, forces in the x. And then you can have as many moment equations as you want. And what we just showed is that you could have as many forces in different directions. Let's say I chose this coordinate system, this new coordinate system. I never thought of that. I could have the forces in this direction have to be 0, and then the forces in this direction have to be 0. So that's also, yeah, that could also be a cool, it would be fun to do a problem where you had to do that. I don't know if there's any problem where you would have to do that unless you set up the geometry in a way where you'd have to use a slanted coordinate system. It'd be weird to set up a problem where you'd have to use both, though. Especially for the summing of the forces in the x and y. The second you actually get the forces this way and that way, I think you're done. You know what I mean? I don't think you can. But maybe that's not true. Maybe that's not true. I could see problems where that could work out. Because that was the question. This student was just like, well, how do you come up with harder problems that are difficult to solve that have... I would say that would be one. Where like, you know, sometimes like things sagging on strings. Like let's say this is a spring. And like this thing sags down. But you don't know how much it's going to sag down. Because it has mass. It's being pulled down. It's going to have to find an equilibrium point. And then that equilibrium point is going to be your vector. And so, you know, I think a cool problem would be like, well, maybe, I don't know, maybe you'd have to sum the forces along that, I don't know. I'm gonna pause there. But yeah, harder problems are ones where springs sag, where they have an initial position before, and then you're going to weight it, and then it's going to be in a new position, and you don't know the angles. Those can be a harder statics problems. Okay, so let's do this graphically. I'm going to just do that on my own and then show you the graph. Alright, catch you on the flip side. Alright, hell yeah. So we're back, and we did a pretty good drawing of this. But the crazy thing is when we go to do the pulley, the force on this isn't directly over this point the way we have it drawn. Now we can get it to be over that point, but that's literally, for me, that is the hardest part of this video. I had to like really think about that. A lot of this stuff like physics and math, I consider it like juggling, especially when things aren't intuitive. And this pulley is hella not intuitive, so let's go over it almost in a textbook standpoint, and in a way where we just can't mess up. So one of the things is that we do the idea of the free body diagram. So let's grab a new sheet of paper maybe, and we're gonna draw this pulley like it's the only thing in the entire universe. And we're gonna make a hole. That's a hole. There's nothing. It's just the chassis part of the pulley. Cool. And then we know forces are going to be on it. We have a 5,000 down, and at a 45-degree angle, we have a 5K. Cool. I'm just going to write 5 for this one. So 5 and 5. This, and what we know about this, you know, the free body diagram method that I do, pretend it's the only thing in a universe, and then you apply the force, it's going to be moving in this direction and that direction, you know what I mean? Or some sort of, like obviously there's going to be a resultant where it's going to be moving in that direction. And I'm even going to take a step aside just because these are tensions. And so if we do have a point, and we have like a tension this way of 5, and a tension this way of 5, the resultant has to be between these two. Okay? Now, it's going to be different is if like we have a point here and we have a 5, and then we have a, like maybe a compression of 5. Now, in this case, like what do we know? Well, we could draw this line of action right here, and if we go this direction, you know, with this tension, the only other direction we can go is this way. So even just right there, we know that the force has to be, you know, on this side of that axis. Okay, so that's kind of one of the fundamentals too. Even over here, then I could also say here, if I have a line of action here, and I'm going this way, 5, and then I have to go this way. Well, now I know that the force has to be on this side. Oh, and I apologize. I didn't even do. I could have done it right off the bat. If I have a tension this way, I can't go this direction. So this is out. This is out. So yeah, even starting right here, I could have drawn a 90-degree angle anyway. I'm going tension of 5 this way, and then I'm going to do a compression of 5. I have to be within this, so my resultant vector has to be within this 90-degree window. And I guess what I'm saying is like, for this, if I don't know, but I do know I have a tension this way. So I have a tension of some value this way, and then I have a compression of some value that way. Then I have to be within this window. Cool. Now let's say I have a compression this direction and a compression this direction. Just any two arbitrary. I guess it's pretty close to a 90. You know what I mean? Now what? Let's do line of action. I can go this way, but I can't go back. So right here is going to be, I can't be over here or over here. You know, so that at least gets me down to 180. Alright, hell yeah. So now I can move this way due to this compression, and then this one I can move this way. So I'm going to be in this quadrant. That's where my resultant vector is. I should have drawn the resultant. So we have a resultant there. We could have a resultant anywhere in this quadrant. Cool. So now you have this idea. I mean, I don't think they explain this like the proverbial they, the textbook they. You're just like, holy hell, no one's going to tell me anything. Is the fact that, I mean, like the classic is like, okay, you have a wall, and you have a wall, and you have like a steel bar. Well, yeah, no, it's got to be on a hinge. So we have a hinge there, and a hinge there, and we got two of these. And now, let's say I put the force anywhere. I'm going to put a force P this direction. I could put, a force P this direction. I could put it in this direction. And now the question is, like, what are these going to be? Are these going to be in tension? Are they going to be in compression? And what this boils down to is we have a point right here, and let's say these are our lines of axis, that this, so along these two lines, I could have so this would be a tension from this one, and this would be a tension from that one. So let's just call this 1, this 2. So I have a T1 and then a T2. Or I could have a compression on that one. So I could have a C1, or I could have a C2. Alright, let's finish up this fairly fast. But the deal is, as long as the vector can be a tension or a compression, it still has to be along this axis. So like this member 2 has to be along this axis. But if it can be in tension or compression, and then this one can be in tension or compression, and so I could go this way in tension, this way in compression. Cool, I can get to that point. Okay, let's continue on. So let's go let's do this one in tension, and then we're going to go this one in compression. Cool, I could be over there. How about this one going in compression and then into tension? I could be right there, compression into tension. So now the question is there any point that I can't reach? It's like no, because I could reach this point right there. I'm going to be a little bit in compression and then a lot in compression that way. Cool, let's go over here. I'm going to be a little bit in compression of member 2 and then a lot in tension of member 1. So from this point, and all these are from this point, if I have a resultant vector going through that origin, basically the center of that point, that's what my resultant's going to look like. And cool. And then I could have a resultant at any of those other locations. So I don't think that gets explained, because that's what's going to happen, in our problem is, well, I don't even know where we're at. Well, I mean, just in general, so that can be the case. If both members can be either in tension or compression, you could theoretically have any force on that member. You know what I mean? I could put a force this direction, that direction. So now let's go back to our I don't even know if this is gonna make sense or not. But okay, so we're gonna draw our pulley. Well, yeah, so with a pulley, so here's the chassis. It's in outer space. We have at a 45, we got a 5K on there and a 5 on there. Now, these are in tension. They're ropes. They can't be in compression. And so the only direction we can have a resultant, and the line of action is going to be up here in the line of action. So we know that the line of action might go through that point. So from this point, we could have a resultant. And, and I guess I should have done this one again. But, so if I start here and I can only be in tension down this path, I can't go this way. So I can even just draw the perpendicular line. I can't go into this quadrant at all. Now how about over here? If I go down this line, I can't go backwards, and so I can't be in this quadrant.
Oh, the stomach's growling.
All right, so I can't be in this quadrant. So that at least from here, I have to move this way. Well, yeah, just from I can't move back. So this has to be I can't move back. I can't move back. I guess I don't know where I'm getting on that, but I mean basically if both of these are in tension, the resultant has to be between there. That's the take-home point, because if I move down this path and then have any sort of tension this way, I'll have to be over here. And so the way I like to do this is like, hey, if I have a couple paths to go down, let's say I have a big force this way, so I'm going to go this way this much, but then I just have a little component that way, so I'm just going to be right there. Cool. Now if I go down this way, is there any possible way to go this direction? No, because I have to add the tension in that direction. So that's where if I go down this path, I can't go this direction. Or I guess if I go down this path, I can't go up. So the only other direction to go is this, because I'm going down this vector, and then I look at this vector, I could add it. And if I could go in the negative direction, I could go anywhere along this line after adding this tension. But I can only add more tension from this vector, so I can only go this direction. So that means I can't go on that side. So now all this space is added. Same thing over here. If I have tension down this side, the only other place I could go is down this parallel path. So there you go. But but I can't go in the negative direction because this rope can't take compression. I can only go in the tension direction. So I can go this way and then this way. Cool. And so the resultant vectors have to be in between those two.
Alright, let's get another battery in.
Alright, hell yeah. So that was definitely not fun. But I just don't think anyone's going to go over that. How like, whoa, if I have, two tension vectors, the resultant has to be in between. If I have two compression vectors, the resultant has to be, they would cross and they would be that way, and the resultant vector has to be in between. And then if, and if I have, let's do this. So if I start right here, if I can only be in tension this way, but I can only be in compression this way, well, then, then just draw the vectors from this point, tail to tip, and it's like they're both in tension. You know what I mean? So then the resultant has to be in between this, that quadrant. But if you were saying if I can only be in tension this way, and I have to be in the compression direction along this parallel line, well, I can't go this way, so this direction's out. And then over here, if I can only go along the compression direction, but then I can go along a parallel line matching this one, but I can only go in the tension direction. I can't go this way, then I can't go that direction. So there you go. So that boils it down. I can only be vectors within that space. So this would be a tension vector and a compression vector, and then that's the full gamut. You could have sweet. So either two similar, like two tension vectors, or two compression vectors, and they're going to be in between, or a. But yeah, just draw the vectors from the point tail to tip, and then the resultant has to be in between those. That's kind of the parallelogram method. All right, so now for the good stuff. That was kind of just the lead-in. All right, for the fact that this pulley has some dimension to it. So we're going to do that free body diagram. It's going to be the only thing in the universe. It's just the chassis. We have a 5 kilonewton there and then a 5 there. But now, if this is the only thing in the universe and we just put forces on it, it's going to be moving in, it's going to have, if we sum the components up, we're going to have a component this direction. And again, this is a 45-degree angle, so we're going to be 5 divided by 1.5, or kind of 5 times 2/3. So what's 5 times 2/3? Don't know, but that's 10. That's 5 times 2 is 10 divided by 3. Okay, so we're going to have like 3.3. So we're going to have a force at least this direction of 3.3, and that's the only force in that direction. F equals ma. Say that we're going to have motion in that direction. This is made of some sort of mass. So we could find that value of acceleration. That's going to be change in velocity. Cool. And then we're going to have 3.3 plus 5. We're going to have 8.33 down, and we would have an acceleration in that direction. And accelerations are also vectors, so we could add them and get some sort of resultant. We know we're going to get a resultant of these two forces in this direction, but the better way to go about something like this, because the first chapter stuff is just like, hey, can you resolve this into, but you would have to do a line of action here and a line of action here, and then say, hey, this is the point of origin of these points. It would be like, and we could do this. I think I need to do this more, where, hey, sure, this is your pulley chassis, but let's like weld massless material to this chassis. So this material doesn't have any mass. The chassis has mass. But then we're gonna have a dowel right here, and then this is where we're going to pull on a string, and this is where we're going to pull on a string. And so that's going to be the same thing as attaching a rope or string to that part of the pulley and that part of the tangential part of the pulleys, how the problem is set up. So I think that is a very good visual for like, hey, line of action. Even though you have this imaginary point, you can think of welding, massless material. And if you don't want to think of that way, just like add construction foam, like high density insulation foam, glue it to this chassis, which is metal, maybe. And so this foam is going to be maybe minuscule mass. You know what I mean? Its mass can be negligible, but it's still a rigid point that you can attach to. I think that is a very good place where your line of action does not intersect with a point on your rigid body. Okay, so that's first up. Next, I think we got to draw that again. So we have the chassis, 5 and 5. But most of these are just way better just by saying, hey, this thing isn't traveling across the universe this way or this way, so there must be some other force in some sort of direction, probably that direction, let's just say it's there, some sort of resultant force that's actually like keeping this thing from moving across the universe. Okay, and that's where we just get the classic equations that, hell yeah, this component in that direction has to balance with and we would call this like the Rx direction, and this would be, or right here, and then the Ry. So we would say, basically 2/3 of 5, and this is 40, we can get more technical, like if this is the hypotenuse, we have a 45-degree angle, and let's say our angle's right here. I always do the sun is shining. So if I'm going to use this as my angle, cool. It's a 45-degree triangle. I could use this as my angle too, but we'll use this one. So the sun is shining. So this is the sine component. So we have 5 sine 45. That's going to be in the negative x direction. So we have negative plus Rx. And we're saying the sum of the forces have to be equal to 0. Until you get used to this equation, and then even right off the bat, it's just like, well, yeah, this is one that you could write. An identical equation is just saying, hey, the force this way has to equal the force that way. So a lot of people just do 5 sine 45 is equal to Rx. And because at the end of the day, here's your variable anyway, and now it's already on the right side of the equation. But I think you would want to start here because this is the classic Newtonian sum of the forces, in this direction means that this thing's not traveling across the universe in that direction. That's the sum of the forces equal to 0. And again, a lot of people don't even explain where this comes from. It's F equals ma. Here's the forces, here's the mass, here's the accelerations. From a technical perspective, it's the sum of the external forces. It doesn't matter if this thing is made up of tightly wound springs and it's just ready to explode or implode or do whatever. It's dangerous to be around. It doesn't really matter. It doesn't matter if it's made out of something like that. The external forces are the force on that rope and the force on that rope. Cool. And that's how we do free body diagram. We chop that out of, once we chop it, we don't care what's happening on the inside, just the outside. But when you do chop something, let's say I have something like this, like a cantilever from a wall, and I put a force down on this right here, and then when I go ahead and I don't even know how to do this, but yeah, if I took this whole thing and then chopped it away, I would have a force down. I would have to have a matching force up, some sort, and that would have to equal. But this is the only place I can have forces. I can't just magically put a force under this cantilever. Can't do it. So cool, I'm going to balance these two forces, but now isn't this thing going to be spinning around the universe like that? But no, it's not. So that this is the idea of chopping away something and then putting it on a separate sheet of paper, pretending like it's the only thing in the universe, and then going back to be like, well, do we know anything about it? Hell yeah, I have an identifiable force on it, so let's do that one. And then where I cut it away, especially if I had to cut through something, that surface is where I'm going to pick up all the other external forces. I can't add other forces anywhere along where there was just air, where nothing was touching anything. And so here's the only place, and that's where you get like, hey, you get this shear force, they call it V, and then you get like a normal force N, but this thing wasn't, nothing was tugging on it this way anyway, so this just goes away. But now you have this P and V that are making this thing spin hella this way. But we know it's not, so we have to have some sort of something that prevents it from spinning this way, and that's going to be a moment in that direction. So that's kind of like the nitty-gritty of how to chop something away. It's a chunk of mass. We have known forces on it, usually unbalanced. But then we know that it's not traveling across the universe in this direction or spinning. And so but the only other places we can put forces is usually where we cut it away. And I probably should get better at did I even do a good job of cutting this pulley away? Probably not. You know what I mean? Because the pulley is this, it's the chassis, and then it's a chunk of rope. You know what I mean? And maybe the rope is massless. We'll just have to assume that. But there you go. This is probably more accurate. Now you have a tension out of this rope and a tension out of that rope. Because, well, I don't even know. That's where literally, yeah, I should. Let's if we're going to do the full video of how do you go from the basics up to this? Well, you would actually take a look at what you know. Hey, I have a chunk of mass right here. So big chunk of concrete and that's it. So cool. And I know it's made of mass, and I know there's an earth underneath it. And I always say no one goes over this from the very basics, but yeah, expect a lot of books will just be like, hey, this load L is just and let's say this has mass. They're just going to say this is mg. And even that might be too much for people. They're like, I don't even know where that comes from. And so it's because anything with mass that's next to something else with mass, and in this case we have an earth underneath us. So it really and that's where it's well, don't you have a table over here, and aren't you doing experiments? Maybe you're up against a mountain. Well, yeah, all that stuff is so negligible that even when we do this equation, it doesn't even matter if you're literally you would have a human body would have I think even maybe as much as an 8-ounce difference if they're on top of Everest compared to just chilling at the beach, just because they're farther away from the center of the earth. So any physical experiments that are done in the deepest trench or at the top of Everest, I mean, yeah, you just use the gravity as 10. All right, but yeah, and where that comes from is Newton's gravitational equation. You have the force of gravity, because right here, this is the force of gravity. You're going to say the force of gravity is weight. In this case, it's this load L, is mg, is 5,000 newtons. Okay, but let's say they didn't say this was 5,000 newtons. They said this was 500 kilograms. That happens quite a bit. They're like, hey, we have a mass of 500 kilograms. Why do we have a force here? Because of gravitational equation. Gravitational constant times the mass that we're analyzing, or the two masses. Basically, the mass of whatever and then the mass of the Earth. But this is the equation that you'll pretty much use all the time for weight, because you have the mass that you're analyzing and it's on the surface of the Earth, and then it's divided by the radius of the Earth squared. And again, this is just the radius of the Earth. It doesn't matter whether you're on Everest or at the ocean. This radius of the Earth will be pretty much the same. It's 6 times 10 to the 6. 6 million meters, probably 6.27 maybe, I don't know. Yeah, I say we should go over this every time, but where do you get the 10 from? You know what I mean? Well, this mass doesn't change, but these three things or I mean the mass you're analyzing is the quantity that you input. So that will change, actually. Gravitational constant, that doesn't change, it's a constant. Mass of the Earth doesn't change, and the radius of the Earth doesn't change. So just these three numbers add up to 10, and I think that's fascinating, because, like, man, they aren't pretty. I use the fact that, like, I don't know, like, physics is, I don't know, Christians aren't into it, so it's kind of like the devil. I probably shouldn't use that. But anyway, gravitational constant is 6.66. It's 6.67, but just think 666 times 10. Now it's to the negative 11. Some things you don't, maybe you don't know that. But now times mass of the Earth, that's 6 times 10 to the 24. Another 6. And maybe you don't know this 24, but we'll get there in a second. Radius of the Earth is 6. 6 times 10 to the 6. That one you should kind of memorize. 6 million meters, close enough, right? We're squaring it. So this becomes 6 times 6, and then 10 to the 12. Cool. This 10 to the 11 actually comes downstairs to be 10 to the 11. And that's going to be 10 to the 23. And you might be like, where are we going with this? Well, now it's pretty easy. 10 to the 24 divided by 10 to the 23. Cool. Out pops a 10. And this is 6 times 6, and this is basically 6 times 6. So those all cancel, and you get 10. I mean, I just find this one so fascinating that it's just like, yeah, you should just do this every time because it's fun. Anyway. Oh, man, I'm glad I'm doing this because this is one that I just don't do, where it's just like, how do we take this pulley and figure out that we had two tensions on it? You know what I mean? We had a rope. Doesn't mean we had tension, maybe. You know what I mean? I don't know. So, cool. We got to the fact that force of gravity is going to be M, and then these three things are 10. 10 is just G. That's what we're going to call G. 9.8. All right, so, nice. Okay, so let's draw the free body diagram of that mass. So we have some sort of mass. We know that we have a weight on it due to the force of gravity. All these things is 5,000 newtons. All right, so we did our free body diagram. We put this thing all alone in a universe. There's nothing else in the universe. It's a chunk of mass, and we put a force on it. Newton's law says that putting a force on this mass is going to make it accelerate. It's going to change in velocity this way. But then we go back to Earth and see that this mass isn't moving, and we know there's a force on it. So you're just like, what gives? Well, we use this idea that there has to be some other force this direction that's equal to this weight. And in this case, that force, and what did we have to do to get the free body diagram? We chopped this mass and we went through the rope. So on the surface of the rope right there, that's the surface. So when we chop this away, there's just air around everything else. So we can't add any forces anywhere else except where we kind of chop through. And a rope is interesting because it can only have a force. You can't have a sideways force on a rope. You can't have a compression force on a rope, but you can have a tension. So there you go. We have a tension in the rope, and that's equal to W. Booyah. Okay, and then we can just go up the line. Now that we know that we have a tension in the rope, and we know what that is, we can start chopping more stuff up. So we can chop what should we do? Yeah, I mean, I guess you could just chop higher up the rope. So then you have this, and then you have a chunk of rope. You still have the weight, and then yeah. So now it just shows that you have a tension just up higher. Cool. Oh man, yeah, pulleys are. Oh yeah, rope's awful. I mean, I just kind of know that you. Yeah, it's so bizarre. I'm gonna kind of pass on this one because I think I need to spend more time on it. But yeah, I just use the axiom that, hey, a rope can only have tension as long as it goes around a pulley. There's no kind of friction in the pulley. And you're just going to have that tension. That tension's going to be the same. But anyway, we got to move on to the juicy details of this pulley. That was like a 30-minute side just to get to the good stuff. Alright, so hell yeah. So the good stuff with this chassis is we have the chassis, kind of this hollow, and we know we have the forces on it. 5 and 5. And we know that we have oh yeah, so here's an interesting thing. Now, we know that it's not traveling across the universe in those directions. So how is it stationary? Like, don't we have to have a force like in this opposite direction? I mean, and this is kind of bizarre. Like, we said that we have a line of action right here. We have two tensions, so the resultant, and if they're even, it must be like directly down the middle. So we do have a resultant that's this direction. So here's our resultant, whatever, some sort of number. That's going to be the force that's wanting this pulley to go that way. We know the pulley's not. Now we divvied this down into one force, so we actually have to have a force that's totally opposite of this in that direction. So that is the force that we get. The only place that's actually touching... Alright, hell yeah. The only place that's actually touching this pulley is the contact point of the pin. So now I'm actually going to kind of draw the pin in. And then how they do it in the textbooks is you just draw like just a lot of clearance. Like way more clearance, a lot of visual clearance. But here's the pin. And this pin, let's say just for the moment that it's attached to the box. But after this, that's where the mental headache comes in. You're just like, oh, we have to do it twice or something. So we have this pin. It's just welded to the box. Cool. So this pin, this pin is providing that force, the contact point right there. And because it's another circle, and this circle's larger, you're going to get a concentrated point right there. So you are going to get a force just right there to balance. And so that is... But now it's going in the wrong direction. That's why just mentally this is hard to juggle. And I don't even know if I'm doing it in the best way possible. Probably not. But cool. But now we're going to... I think to think of this pin as like a welded corner on this box is also now mentally not the way to look at it. I would then say we're going to draw the corner of that box, and now the corner of this box, we're just going to drill a hole through it. Cool. And then we're going to slide this pin into that hole. And when we do that, how are we going to do that? Yeah, when we do that, this pin, I mean, this is the back and forth. It's just like, okay, this pin is going to be on that upside of that pulley, but I mean, then just look at your overall. We have this pulling down and this pulling that way. So if this pin is just loose, and we're talking like, hey, maybe this box has some depth, so this is maybe a whole bar all the way through that, so it's not going to fall out or anything like that. And it's sticking out maybe. But when we put all this downward force on it, that pin is going to rest right in this corner. Okay, so now let's try to draw this corner with the hole, with the pin, and then this pulley. So this pulley is going to be like this. And so that's what we have. And maybe we should try to draw it one more time where we have the hole, we have the pin, and then the pulley so here's our pulley, here's our pin up against, so this pin, so the pulley is being pulled down, but then the pin is being pushed into the corner of the hole on that, it feels like you're doing like the hole in the bucket song, you know what I mean? That's the hardest thing I think about statics is like, alright, so it's kind of the whole concept of like if I'm pushing down on the earth's pushing back up on me or something. But for me, that was enough. It's like, I think that's mental juggling enough, but it made sense to make the pin loose. Because if I welded this pin to the box, it's just like, well, it feels like the force is going up. You know what I mean? You're like, what gives? If I push down, like something has to push this, because we know the chassis is just floating. And we got two forces this direction. So we must have to force up because it's not traveling through outer space. And then if that's the case, we have to have, I guess, the weird thing, the fact that this pin puts an upward force onto the chassis means the chassis, means if I like the chassis, so if I draw the pin, the chassis pushes down on the pin. And I just have a hard time seeing that. I think I can say it, but doing this drawing helped. It was just like, well, I don't believe you. So let's, I know that the pin has to push up on the pulley. And so I'm going to be done with that aspect. But then I'm going to make a pin loose in this setup. And then I'm seeing that, yeah, this weight, this cord is attached to the pulley, and the pulley is pushing down on the pin. So there you go. I drew the pin, and now that made sense that the pulley, that whole assembly is pushing down on the pin. But I see where it's coming from. I can see the chassis is pushing down on the pin because from the overall picture, this weight, this tension is pulling down on the chassis, is pulling down on that pin. So there you go. That pin is right here. Then it's a part of a bigger hole inside that corner, you know, like chopped out. And it's going to be definitely resting in, if this is the direction of that force, it's going to be contacted right up against that point, concentrating that load. So it's like you can take, so it's going to have a line of action. It's like you can take a compressive force, or I mean, in this case, it's going to be a tensile force because it's like I'm drawing. It's like, well, I mean, either way, like you could weld a stick to it and push on the stick this way, or just have a dowel and then pull with a string that direction. That's going to be all the same. So, hell yeah. But yeah, you're going to have a downward force in that direction. And I guess the take-home point is it's going to go right through the center of that point. So that's where it doesn't matter how big this pulley is. The line of action is going to be like right there. You're going to have an equal tension. So you're going to get a the parallelogram says we're going to go equal distance this way, and then we're going to be going down this path this way. So that's the parallelogram. Or we're going to be having a tension this way, you know, an equal amount, and then we have to go a parallel direction to that one. So two ways to get there. So the resultant force is going to be, down this way. On this chassis, we need some sort of force to balance that. It's going to be equal and opposite. That's going to be coming from the pin onto the chassis. But then when we analyze the pin itself, or just the box with the pin on it, that means the chassis is pushing down on the pin with that tension. And that's going to be right there. And holy Toledo. So now we should actually get an equation for that. Yeah, I guess we didn't even do it. We didn't even get an equation for that. I don't think we're going to run into any issues. We have a 45-degree angle. We have 5 and 5, or 5K. We know that this resultant, I mean, we already did it, but the resultant has two components, an Ry and an Rx. We have Rx is equal to 5 sine 45, and then we have Ry is equal to 5 sine 45 plus 5. You know what I mean? Because we're adding this component. So this 5 right here has a component down and over that's 0.707, or 70.7% of 5. Sweet. So, and that's what 5 sine 45 is, because sine 45 is 0.707 times 5, and that's 70% of 5. Cool. All right, so that's going to be Rx, and then Ry is 5 sine. So I'm going to store that as x, and then 5 sine 45 plus 5 stored as alpha y. Cool. All right, so, and that's going to be our resultant, vector here. Oh, bummer. It's, I didn't do a coordinate system. So if I do a coordinate, this is positive x, this is positive y. And so obviously this tension is going to be negative this direction and negative that direction. So, and this is going to be negative. So these are both going to be negative, negative. Oh man. Still not doing it right. Holy hell. Again, we have this idea that some of the forces in a particular direction have to be 0. So some of the forces in the x have to be 0. So this is a negative 5 sine 45 plus Rx is equal to 0. Cool. So yes, you get Rx is equal to 5 sine 45. Let's do the next one. So now we have a negative 5 plus 5 sine 45. So this minus 5 sine 45 is equal to Ry. Okay, so, cool. No. Plus Ry is equal to 0. Yeah, so we get the same thing, that Rx is 5 sine 45 and Ry is 5 plus 5 sine 45. I don't know why I was tripping out. Just these were in the negative direction. That's what I missed. These are in the negative direction. Has to be balanced by something in the positive direction. Sorry about the sign confusion on that. So we have this. This direction is going to be 3.5, and in the y direction, it's going to be that 8.5. Cool, and we got that x and y in our calculator. That is what the chassis is going to have to, the resultant. The only way to keep the chassis stationary in the universe is if that pin is touching it and pushing exactly in that direction. And that's what we find. And then we know that that pin, let's say it's loose, is also being pushed by the chassis equal and opposite. Yeah, so what is if I'm going this way in the x direction, 3.5, and then up 8.5, what's equal and opposite? Well, aren't I going down 8.5 and then over 3.5? Hell yeah. So now, the actual tension or resultant on that is going to be, so I got to go negative y, stored as y, and then negative x, stored as x. Okay, so x and y. So there you go. So holy Toledo. So now off this point, instead of having a tension this way and a tension this way, I can say that my tension is going through that point. It's going to be at a 45-degree angle. How do we prove it's a 45? Like we know it's going in the negative 3 and then negative 8. That's where we use the tangent. So if I draw this, if I if I draw that that in, and I'm going negative 3.5 and then negative 8.5, the angle here is going to be inverse tangent, because the tangent of this angle, tangent of the angle, draw your sun is shining. This is going to be the sine component. This is the cosine component. Definition of tangent is sine of that angle divided by cosine of that angle. Well, and then, yes. And this dimension is the hypotenuse times sine of the angle. You know what I mean? We just said that this dimension is a percentage of the hypotenuse. And sines and cosines are percentages of the hypotenuse. So, like, this dimension is the hypotenuse sine theta, and this is the hypotenuse cosine theta. And so those cancel. And so just at the end of the day, tangent of an angle is just the sine component divided by the cosine component, or it's just this whole dimension. This dimension is the hypotenuse times sine of the angle, and this is the hypotenuse cosine of the angle. I'm just using this number as like, hey, hypotenuse is the bigger number.
All right, booyah.
So we can get the angle, and it should be 45, hopefully. Inverse tangent of this is going to be the x divided by the y. We get 22. Oh, my bad. My bad. I did not see that one coming. I knew something was up because I was just like, hey, this doesn't look right. I'm glad I did that in my calculator. Yeah, no duh. No. Yeah, so we're going down 5,000. And this is where doing problems like these graphically, like, you can just, like, especially if you have a bad assumption in your head, it's really good to do things in a bunch of different ways. So we just said we had 5,000 down, and we had 5,000 at a 45. We'll just quickly do that. Just like go right here, go 1, 2, 3, 4, 5, and then at a 45 degree angle, do 1, 2, 3, 4, 5. And then draw, you know, a line there, and then just kind of see what type of angle that is. So, I mean, here's going to be a 45, and look, it's about halfway. So there you go. So right off the bat, I could just be like, yep. So I'm glad I did that because we have an angle here. Oh yeah. And I mean, what we were. That whole process was just once we started to sum the moments about this point. You know, we don't want to figure out where this distance is. We're not even given the dimensions of this pulley. So at least once in your life, you have to go through the whole process that I just did. And I probably didn't do it as good as I'd want to. But no, I'm satisfied with making the holes big. Because that is something they do in the textbooks. Like, you know, with pin connections. That's why all these pin connections are pushing, you know, into this rigid body. Just like right on the contact point. Where you're not getting any sideways, you know, and it's concentrated load right in that direction. But yeah, if we took this moments from here, we would have to go over to this one, and we would have a negative moment, and then we'd have to go over to this one. But now we can just, right here, draw in a vector, and I might... let's see, how do I even draw that in? So we have x, and then y, and let's see, what would that even mean? We're gonna have down 8.5. Okay, that's about 0.5, and we got 1, 2, 3, 4, 5, 6, 7, 8. Cool, and then over 3.5. All right, I'm just gonna rough this one in. I don't think I have to get too technical. There you go. So we have this resultant, and then the other thing is, hey, we need to figure out what that resultant is. Oh, and I used 5 to represent 5,000. So I got to multiply these by, so I got to go x times 1,000, stored as x, and then alpha y times 1,000, stored as alpha y. Cool. So x and y. So we have 3,500 newtons that way, 8,500 newtons down. And this is I'm going to pull out a sheet of paper. All right, hell yeah. Our first sheet of paper that we did just to kind of get the idea. Now, we used the solutions, but we kind of went from I think we could have got these numbers without the solutions. But maybe not. I don't know. But hell yeah. You know, we had this 8,000 down and 3,000 over. You know, and it's just kind of a nice double check on reality. Because I swear, once you get precise answers, I lose my mind. It's like that. It's really hard for me to look at something and just, you know, round off all the numbers. But hell yeah. So this is what we have. We have that down 8,000 and over 3,000. And it's negative. And we now we have an actual number on this. It's negative 8,500 and over negative, and over that direction 3,500. Cool. All right, let me put that over here. And cool, so we have it. And now what's the magnitude of that? That's just the components. Maybe we just want to know the magnitude. Well, I'm actually going to just write in the components. And I like to do just open arrows, just so then you're not confusing like 3 arrows in a row. Yep, and I'm going to write these in. So we have 8,535.5. This is stored as y in my calculator. And we have over 3,535.5. This is stored as x. All right, that was like an hour too long just to show the pulley, but I thought that was the place where I was just going to there's the one guy on YouTube that does the full statics course. He's got about 1 million views. He does a Mickey Mouse voice, and but I watched his video on him analyzing a pulley, and I don't even know what video it was, but it was one of the more advanced problems, and it had like a pulley in here, and it's just like, yeah, you can't. I mean, you have to figure out some way why the force is directly in the center and get the force down the center and not have it on the pulley, because it just makes finding the moments to those distances just a pain in the butt. So you really just want to get down to one vector, or in our case, I might want to use these because I can just go up to here and say, hey, if this is the point, which is perfectly on here, I just know this is, and on this grid paper, each of these squares is, you know, this 1 inch. 1 inch, or 25.4 millimeters, is going to be my 1,000 millimeters on my paper. So this is 5,000 millimeters, and there we go. We have 1, 2, 3, 4, 5. 5 inches is 5,000 millimeters. That's basically what we have. 1 inch is 25.4 millimeters, is 1,000 millimeters of this. Cool. So yeah, so when we take our moments from this point, I guess we got A, B, C, there's no D, so we're going to take our moments from D. And hell yeah, so now we can just go over 2,000 millimeters times Y, and then we can get this one, like, and that's where, yeah, I have this kind of drawn, I shouldn't have drawn it like that, because it's just like, well, it looks like this force is way the hell down there, and it's not. It's going to be right through that point. I'm not going to mess up my drawing again, though, so, but obviously this tail to tip goes right through there. So we're going to have another negative moment that's going to be 1,000, 2,000, 2,500, and then multiplied by x. Okay, so now we can start summing the moments. Now, and again, like all I did, now we can get back to this graph of like, yeah, that was way too long to get here. But it was, I'm glad I spent so long on that pulley. That might have been the hardest part of this. If you've never done one of those, you're just like, well, how the hell do I get the resultant right on that point?
I mean, mainly, how does it make sense? Cool, and I think we did that. Okay, so we took these two supports, and we followed their line of action up here. And based on geometry, you know what I mean? This is at a 45-degree angle. And so, and this is 3,000 over. So we can take this, this is a vertical line. So if I go 3,000 over, I got to go 3,000 up. So this is 2,500. So I'm going to be another 500 up here. And that's where I'm going to cross this. But it's at least at a place. So, so yeah, this is 500. And so from here, we're over 3. 1, 2, 3. And then up 1, 2, 3. So that's our point right there. It's just 500 above the box. So again, that's where I say, hey, like glue on some lightweight foam, and you just now have added maybe no mass to your object that has mass, and then made it a rigid point to attach this fixed place where you can actually put compression, or like compression from this one would just be a string pulling from that direction. And then, and yeah, so our answer is going to be, this is in compression. So that is going to be a downward. So on this member, we're going to have a downward force from D. That's going to be this. And then S2 is in tension. So that's going to be pulling this way. So we're going to have like kind of a rope pulling from D this way. All right, hell yeah. But because we took our line of action up to this, when we sum the moments about D, these two forces, whatever they are, go through D. So like opening a door, that's like having a door. Here's the hinges. These two forces are like, hey, trying to push on these hinges. You're not opening the door. This is the only force that opens the door, S1, and its distance away. So it's the only force generating a moment, and its distance away is this perpendicular distance. So then I just measured this, and this came out to be 45.5 millimeters. And that's this, 1.791 inches. Millimeters to inch is an exact, 25.4 millimeters is exactly 1 inch. So I just divided this by 25.4. That gets me inches. And then, on my paper, 1.1 inch is 1,000 millimeters. So I have 1,791.3 millimeters to be this distance. So back here, when I get this point to there, and then I do, then I have this S1, which is in compression, and so it's like pushing into this object. So there's S1. Its distance away is going to be that 1,791.3 millimeters. Cool. So the moment is going to be S1. So here's my point D. The moment's going to be a positive S1 times 1091.3. And the only other moment is going to be generated by the two components right there. And we're basically getting there. Because once you solve for, once you get one of the components, hell yeah. Then it's just like, I don't know where... it's just like we went over this scenario where, like, hey, let's say this isn't here. I have a force, down on or anywhere along here, and we have two components here, and if I sum the moments at B, these components go away, this component goes away, and all I have is the S1 component in this direction, and then added with the moments of there. So I think that's also something that's very useful in problems where you're just like, what the hell did we just do? Well, we solved for this. We solved for the magnitude of that force. And we already know its direction. And so then our problem just gets, simpler. Now we have these two forces, and we can kind of do the same thing. We can, figure out which one is best to sum the moments from, and we'll add the two components here, like one component will go through that point, one component will be over there, and then we'll have this distance away. This has to be either negative or positive, but that's the moment on this one. So I'm going to sum the moments at S2, and then we have the two components here. And since this is offset, we'll have and then what that's solving for is this S3. Once we know S3, then we can go through that same process, but we might not even need to, because then we can probably just use sum of the forces in the y have to equal sum of the forces in the x. So that's going to be our strategy to finish this off. Hell yeah.
Alright, hell yeah. So we're back, and I just realized that this is a total guess. We're just doing it graphically, but that's an okay way to get a correct answer fast. So but what we're gonna do is we're gonna go back and be like, well, how do we get this distance? And I think we have to use that's where you want to use, I mean, you got with statics, you have the dot product and you have the cross product. And so one of those, is probably pretty useful in figuring out distances like that. And that's just where it's just like, hey, I'm limited. I kind of know what the strategies are, but I would just rather go for a graphical perspective and then go back and then figure out exactly. I mean, I would like to stumble more across, but in that I'm going to have to use one of those, and then use vector analysis. I mean, basically just use the cross product or dot product. All right, let's get on with it. All right, so we're going to sum the moments at D, and I think we can just go for it. And I should probably just pull out a sheet of paper because I don't want to get this one too crazy. And yeah, what were we doing? Well, we were going to say we have a positive moment from this S1. Well, and like I said, I guess we're going to have to, we did have the solutions, and it told us what direction they were, so that was probably pretty useful that the professor gave the solutions, because we know that this one is going to be in compression. So we know that this vector is going to be that way. Cool. We also know that this vector is going to be that way. What else? We know that this vector is going to be that way. Alright, but let's do it. So we're going to have a positive S1 moment about D. And this is going to be, has two components. One is this way, that's a negative, and then one is that way, that's a negative. Alright, hell yeah, let's do it. And I'm just going to say instead of saying the sum of the moments about D is equal to 0, where I say we have a negative S1 times this distance plus these times their distances. These are positive. No, this is positive, these are negative. I'm just going to say that the negatives are equal to the positives. I think that's just a cleaner way to go about it. So we're going to say we have the force S1 times this distance, 1,791.3, is going to be equal to, we have, now the distance to, how about to this one? That's going to be 2,000 millimeters. So we have, this force is going to be 8,535.5, that's also y in our calculator, times 2,000, plus, now this one, we have 3,535.5, and its distance down to here, what is that going to be? We got 1,000, 2,000, that's 2,500. Cool, and now I can solve for S1. So I'm going to take alpha y times 2,000 plus alpha, this is alpha x in my calculator, times 2,500 divided by, oh, and see, I already messed up because like these are in the negative direction.
and yeah, my calculator, I have x and y to be negative, but I'm saying that they're positive. You know, I'm taking the absolute value of them. So this, I hate negatives, but anyway, so this I just have to multiply by a negative. So I have that is my moment from those two, and then I'm going to divide it by this distance, 1,791.3. And cool, so S1 is going to be 14,464 newtons. And what was our guess right here? 13,000 squared plus 7,000 squared, square root that. Yeah, so our guess was 14,764. So hey, we're pretty much right on. And so that's pretty cool. All right, so the next step will be now to sum the moments about, we're going to call this E. And cool. Let's do it. Now S1, we know yeah, how do you do something like that? I mean, do you do this? You say this is a 1, 2. But still, this doesn't give you the full picture. Because if I want to know this component, I have to say this hypotenuse. I mean, because ultimately we'll try to get into the square root, so let's start getting there. But yeah, this is a 1, 2 triangle. But we want to know the percentage of this side compared to the hypotenuse. Well, we need to find the hypotenuse. Hypotenuse is Pythagorean's theorem. This squared plus this squared. And that's going to be 2 squared plus 1 squared. Hey, that's 5. Cool, square root of 5. So now this side is going to be 1 divided by the hypotenuse. It's going to be 1 divided by the square root of 5. And then this side is going to be 2 divided by the square root of 5. And now we can kind of see, like, hey, do we have any square roots of 5 right there? So we can kind of see where these values come from. Obviously, we might have a lot of square roots of 2. Oh yeah, this was just a square root of 5 that we were, showing. And this is S1. Look at that. S1 has a square root of 5 term. Booyah. So, hell yeah. And then a 45, S2 is a 45, and that's going to be a square root of 2 term. S3 was a square root of 2 divided by 2. So you can see how, hey, the denominator is more. We still have a square root of 2, but hey, maybe the denominator is more because it's a square root of 2 term divided by 2. Cool. All right, and these components anyway, 0.707 is square root of 2 divided by 2. So it is good. I mean, I guess for a problem like this, you got to know where that comes from. And the square root of 2 is 1.414. Half that, well, that's just 0.707. See how this is 14 and this is 14? So there's a lot of different ways to memorize these decimals to 3 digits. I think everyone needs to know that square root of 2 is 1.414. And it's like 0.14142. But booyah. I mean, just you're at 14, 14. Do you see that? And then you got 7, 7. All right, so now we know the percentage of S1 because we calculated S1, but we just need to know the percentages in these directions. And let's figure this. So we got 1 divided by the square root of 5. That's going to be 44 or 0.447. 2 divided by the square root of 5 is 0.894. Cool. If we want to rationalize these, we got to multiply both sides by the square root of 5. That's like multiplying by 1, and then square root of 5 times square root of 5 is 5. And then we just have square root of 5 divided by 5, and this is same thing. We're going to have 2 square roots of 5 divided by 5. So those are the rationalized versions of that. Okay, let's get on with it. So we're going to sum the moments about E. And yeah, we knew that we had components here of this, down in this way. And I'm going to flip my paper this way. We have S 14,464. So we have S1 is 14,464. Yep, cool. And I better store that in my calculator. Store it as alpha S. Cool. So the moment from that is going to be the distance up to there. This is 1,000, 2,000. So we got 2,500. That's going to be a negative moment. So sometimes I just write to, like, you know, maybe make a negative sign. I'm going to have this alpha S. This component in this direction we said is going to be that 2 square roots of 5. So we got 2 square roots of 5 times that this component S. And the distance is going to be 2,500. Cool, that's going to be a negative component. This component goes right through E, so hell yeah, we're just good to go. This component goes through E, so we're good to go there. Now we have S3 is positive, and then this component is a negative, but this component's a positive. So let's get this negative component. We have the distance over here is 1, 2, 3, 4, 5. So we're going to have another negative component. It's going to be this alpha y, and it's going to be 5,000. Cool, so that's going to be a negative moment. This component of this pulley is going to be above E, and it's going to be above E by 500. Cool, and that's going to be a positive component. So now I can put equals to, that's going to be that x term times 500. That's going to be a positive moment. So we're saying the negative moments are equal to the positive moments. And then S3, since we have this drawn right, is going to be a positive moment. And, I mean, even right here, S3 is the only thing we're solving for. So if we got the direction wrong, that's where it would spell itself out. You know, we could say S3 is a negative moment. Put it on this side, and this side would be too big, and so we would say that it would be a negative moment, which means it would have to be a positive moment. It would have to be in that direction, not this direction. But we already know it's in the positive moment direction. Distance over to it, 1,000, 2,000, 3,000. And so we have S3 plus 3,000. Cool, now we just need to solve for S3. So here's our negative moments, here's our positive moments. Alpha S, 2 divided by the square root of 5 times 500. Man, hopefully I'm doing this right. Sometimes, you know, this should work out, though. That's the same thing as alpha S. Whoops. Alpha S times 2,500 times 2 divided by the square root of 5. Sometimes just order of operations, it's good to just double check yourself. No, because we're getting, that's bizarre. I thought this square root of 5 multiplied by 500. Oh, well, we're not multiplying by 500 anyway. We're multiplying by 2,500. My bad. So yes, I had an error in here. I'm glad I double checked that. Cool. So yeah, so the order of operations on this was just fine. If you have a divide by, the next term after it gets divided, but then after that, any next terms get multiplied. Cool. So now we're going to add alpha y to 5,000. Okay, so that's the negative side. Oh, and again, this x and y term, I gotta get this x. I gotta do negative x, stored as x. Now my x term is gonna be positive. Oh, that's gonna drive me crazy. Stored as y. Okay, so now these two terms, sure, they have negative directions, but they have positive values in my calculator now. So even though they're in the negative directions on the paper, they still have positive values in those negative directions. Holy hell. That's probably the hardest thing Where, I mean, I bet you some people are just like, no, we are going to draw these in the positive direction. But no, in general, you should probably be drawing, like the literature says, if you for sure kind of know the vector is in that direction, you should draw it in that direction. It could be useful just to draw vectors all in the positive direction, but not when you have like pulleys going down. It'd be weird to draw the tensions going that direction. And then have negative values for them. That would just be a weird picture. Okay. So yeah, we gotta redo this one. So we have this value plus alpha y times 5,000. Cool. I'm going to store that as alpha g just on this side. But now we're going to subtract x times 500. And then divide by 3,000. Alright, sweet. And I'm going to store that. This is going to be S3 now. So I'm going to store that as alpha u. S, T, and U will be S1, S2, S3. Uh, 24,417. And this is my favorite, kind of satisfying. Is like, hey, we already did this. We already said, hey, this is about 25,000. And then when you get something that's close, man, that just makes you feel pretty good. Like you didn't have any errors. And even if you did, it's just like, hell yeah, you're just at least on the right track. Okay. So now that we know S3, we can sum the moments about whatever point we want and find S2. And it just makes sense. When we sum the moments about E, like, hey, one of the components of S1 dropped out. And, I mean, isn't that right? Didn't we just have this this component this way? 2 square roots of 5 times this 2,000. And we didn't have this component. Then we went right over here to this component. And that was equal to this component plus this component. Sweet. So now when we find S2, we're going to sum the moments about here. So I'm going to call this point F. Let's get a fresh sheet of paper. And we might be able to do this a little bit faster now. When we sum the moments about F, like S1 goes away, this is going to have a component this way and a component this way. So this component goes away. And let's do this one first. So we're going to have negative moments, 2,500. Sometimes it might be just better to write that first. Write the distance first. That's what I see. And then I have, and let's figure this out. Because isn't this a 1-1 triangle? Like, I don't do this that often because I try not to get precise answers like this. I don't know. I mean, I guess it's useful for tests and multiple choice exams. Cool. So what's our hypotenuse? 1 squared plus 1 squared. It's going to be the square root of 2. So now the percentage, or I mean this, if this is my hypotenuse in this direction, if that's my vector, this percentage and that percentage, this is going to be 1 divided by the square root of 2, which is 1 divided by 1.414. Oh, so I think I said square root of 2 divided by 2, and I was wrong about that. No, it's the inverse of the square root of 2. Square root of 2, but isn't square root of 2 divided by 2 the same thing as 1 divided by the square root of 2? Yeah, that's a good one to do, because why is that? If I have 1 square root of the 2, well, it's just not rationalized. The denominator isn't. So I can go 1 divided by the square root of 2, and then multiply both top and bottom by the square root of 2. It's like multiplying by 1, and so this just becomes 2. Square root of 2 times 2. And if you want to do this in a couple steps, anytime that you have everything underneath the square root, or at least a couple things, and you're multiplying them together, the two numbers can go inside. And then
Alright, my calculator cut out, but hell yeah, we didn't get too far. So yeah, two numbers inside, and then so this just becomes the square root of 4, and that's obviously 2. Cool. Alright,
heck yeah. So now we're on a roll. we're going back to here. So now that we know this component, well, is going to be either 1 divided by the square root of 2, which is 0.707, or it's 2 divided by the square root of 2. I'm sorry, square root of 2 divided by 2. You know what I mean? Because, yeah, rationalize this in your head. You got to multiply top and bottom by the same number, because you can only multiply it by 1. Because we can't change this number. That's important. You're going to have the square root of 2 upstairs, but that's cool, because you're rationalizing the denominator. And you'll have the square root of 2 divided by 2. All right, hell yeah. So let's, so we have this distance, and we have this vector, and we have a negative moment. We already showed that. And we're going to have S2 divided by the square root of 2. There you go. I'm just going to take this times that, put this upstairs. All right, so that's that one. We're going to have S3. We already know what that is. I really need to store S3 in my calculator. Oh, I already did. Alpha U. Cool. Got it. So I know what this is. I'm going to sum the moments. So this force, if I'm starting at F, going in a perpendicular line towards S3, sweeping my fingers in the direction of that, I get a positive moment. And it's going to be 1, 2, 3, 3,000. It's going to be a positive moment, so let's go over here. These are the positive moments. So I have 3,000, S3. That's perpendicular, so we're just good to go. All right, now I got these two again. Which one do you want to do? Let's do this one is negative. They're both negative. Both on this side, so we have 1, 2, 3, 4, 5. So we have 5,000 as our distance, and y is our letter. And then we have, this component is going to be, oh, now we're just 2,000. Sweet. And we can come back to here. I mean, obviously it's just 2. So there's a lot of things just from here you can be like, 2,000. But this is a nice representation because I know it's 100% accurate. This drawing isn't accurate. You know, it's not, I don't think that drawing is 100% drawn in AutoCAD. All right, where were we? Yeah, so we got 2,000 times this x value. All right, that's going to equal, and that's it. So we have some of the moments here. We have the one component this way. This one goes through F, so it's not part of a moment. S1 is going to be positive. And then this one's negative, this one, and both these two components are negative. So we got 25,000 alpha S2. Oh, weird. So did I haven't solved for S. Oh, my bad, sorry. We're solving for S2. We don't know it. But we know everything else because we know S3. S3 in my calculator is stored as alpha U. Okay, so I'm going to start with this side. We're going to be 3,000 times alpha U. We're going to subtract these two. So we're going to subtract 5,000 alpha Y. Subtract 2,000 alpha X. Whoop. Cool. So I got both those over to this side of the equation. I'm going to multiply by the square root of 2. And then divide by 2,500. And we have, and I'm going to store this as alpha. So S2 is 13,296. That's alpha T. And then here is our, and then is that going to be about right? So we have 10,000, 10,000. We thought it was 13,000. This is going to be 10,000 times 1.4. I mean, that was our guess. 10,000 squared times 2, square root that. Yeah, we thought it was going to be 14,000. 1.414. But hey, we're pretty close. Cool. And obviously we're solving for the exact answers. Now, the take-home point was we just assumed this distance, but that's what gave us accurate answers, so I'm totally satisfied with that. You know what I mean? If I'm just trying to learn this stuff and just always be kind of working towards something, I'm going to try to find methods that still allow me to continuing on. And that was the take home. Like, hey, let's say I don't know how to solve for that distance. Well, just pull out some graph paper and estimate it.
I bet you'd still get quite a bit of credit for this problem if you did that, instead of just turning in nothing. Alright, hell yeah. Now, I didn't even realize we can have a moment of truth. You know what I mean? I can store 5,000 in my calculator as alpha L, and then we can actually do these. So I'm going to do, man, these are ugly. But I'm going to do the inside first. Square root of 2 times 9 plus 8 times the square root of 5 divided by 16 times alpha L. Okay, 14,484, that's going to be S1, that's going to be alpha S. And heck yeah, we're pretty close. So I'm actually going to store this as alpha N. That's the right answer. Cool. And then we got alpha S. So I'm going to go alpha S minus alpha N divided by alpha S times 100%. Hey, we have a 0.1% error. So there you go. Like, I'm just not a big fan. I mean, I think this is twice as much work for me, but it's a good skill. I'm not going to do this right off the bat of just like always keeping things as mathematical equations. I don't think it's good for my learning, and I don't think it's good for anyone's learning, honestly. I mean, I think graphical, numerical answers, I mean, that's why I'm making videos that are centered around them, because you can take a complex problem and still generate solutions. And I don't know, like, it's pretty satisfying. And if everyone started to do it, yeah, maybe it loses its luster. I mean, but the fact that no one wants to do it because, what do they think? It's like a form of cheating, or just like it's not an accurate answer? It's like, hell yeah, it is. And most of these equations anyway, when you get something crazy like this, it's only applicable to this scenario. And it might only be applicable to this scenario when, like, you can't change much. You didn't say that this could be pulled at any angle. You know what I mean? So, like, even though you're getting equations for things, they're so limited. And it would be very difficult to, like, tweak something on your problem and still, like, not mess up your, what you think is, like, hey, a pretty decent equation. Like, all this equation is like, hey, all we can vary is the load. Cool. Like, you can have this exact setup, vary the load, and then sure, you can vary your solutions. But, I mean, who cares? Yeah, that brings up a good thought, because, yeah, this is a who cares. Because, like, why wouldn't you just say, hey, there's an angle S1 here. You know what I mean? So you could have an angle S1. You could have angle S2, or just angle 2, and an angle 3, like right here. And then you could have these solutions with those angles built in. So then you could still have this same shape in the same orientation right here, but then you could change the direction of these members. And I think that would be pretty cool. Because then you could actually, like, even change this one. S3, it would be very valuable to pin this thing right underneath. And then you'd have a pulley going straight up and straight down. So then whatever load you put on would double right on this. And it would no longer be in that direction. So I think that would be pretty decent. And if you had this angle, then you could actually do more than 90, and that just means that the pulley is being pulled this direction. You know what I mean? Maybe the load's on the other side, and you're pulling this way. So also, that changes the problem. That's going to change every component of it. So, like, yeah, this isn't impressive to me. It's just an impressive thing to, how do you then go back and figure out why you have percentage. And I still, it's very important to think of the components, whether it's the sine component or the cosine component, however you think about it, but they're percentages of the hypotenuse. And even though you're getting a fractional number, like between 0 and 1, still, this is, I like to think of it as a percentage. So yes, I'm seeing 0.447, but in my head, I'm saying 44.7%. I'm saying 89.4% in this direction. Because the more you get used to that, you're like, oh, yeah, no duh. Like any angle that's less than 30, like this is very close to 90, almost 100%. Most times you can just assume that this component in this direction is about 100% of the hypotenuse. Cool. But yeah, if you just have a decimal, I don't think the human brain pays attention to decimals too much. You're not being like, oh yeah, that's very meaningful. But hell yeah, 45%. I think people can remember that. So yes, and these triangles will come up quite a bit. You have a 1-2 triangle. Okay, 45% in that direction, 90%. This is very close to 90. This is very close to 45. So 45 and 90. Cool. The angle is going to be the harder part to get on that one. That's going to be inverse tangent. 1 divided by 2. I don't know, 26.5? I bet you could memorize that though. 26.56. 26.565. But anyway, yeah, 26-degree angle. Yeah, because the other, you know, if you're going this way, a 1-2 triangle is 26. If you go the opposite way, a little bit bigger than 30, you get into a 3-4-5 triangle. That's going to be inverse tangent is 4 divided by 5. No, that's not right. It's going to be 3 divided by 4. And then you get 36. So there you go. So go down 1, you get 26. Go up 1, you get 36. 26 and 36, maybe those are numbers you can remember. I mean, but because how many common triangles are you going to come across? You're going to come across this one. It's a 1-2 triangle. You're going to come across the 3-4-5. Yep. There's not too many more triangles you're going to come across. All right, so now what? I kind of don't know where to go. Oh, we were just checking our answers, so let's continue doing that.
Okay, so we have the square root of 2 times 4. And again, we're checking our answer, but we still have a long way to go. Because we totally just guesstimated this difference. We're going to figure out exactly where that comes from. But yeah, the hardest statics problems are the ones that are just word problems with vectors. So they're just like, hey, you know what I mean? All right, so we have times alpha L, and we got 13,000. This is going to be stored as alpha O, alpha T. Yeah, so these are very close. Alpha T minus alpha O divided by alpha O times 100%. So yeah, another 0.8% error. So our accuracy is so good. So this is pretty sweet. And the only graphed point on here was this distance. You know what I mean? And we got it fairly accurate. And if I can print out 11 by 17 with Photoshop on grid paper. So technically I could redo this and get a more accurate answer for this distance. And then just plug and chug again to get better numbers. But like all we're getting is decimal numbers for S1, S2, and S3. But that will help us when we go back and figure out how to generate, you know, these nonsensical numbers. All right, last one. They're even just hard to write in your calculator. Let's see if I can do it all in one go. I'm going to have negative. I do need a parentheses. 27 square root 2. Plus 40, another parentheses divided by 16. But even right here, now I can just do alpha L. This L is not going to be divided by 16. You know, this is not the same as parentheses 16 divided by L. Calculators will only do divided by the number and then multiplied by L. And, you know, it's not going to be divide by 1 and then multiply by 6. No, it's going to take the next, anything after the decimal, anything after the quotient, it's going to do that operator. It's going to divide by 16, but then it's going to multiply by L. Cool. And that just means it's in compression, and we're going to store that as alpha P. And alpha U is 24. So there you go. So those are 24,400, very accurate. Alpha U minus alpha P divided by alpha U. times 100. Yeah, so this one was very accurate. Oh, and that makes, no, I don't know why that makes sense, but whatever. Okay, hell yeah. So now we did it. We got the three forces. I think, like I'm going to say it again, the take-home point for me was like, start out getting an idea of what the problem is, guesstimate the answers, because it's just going to be so rock solid when you actually go for the exact answers. And now we even have a double check that we actually did all the moment equations. They weren't that hard, honestly, but now I have to. I'm going to take about a 10-minute break, and then just be like, well, how do I get this again from a vector perspective? And then we'll probably come back and try to figure out how to get these looking like those.
All right, catch you on the flip side. All right, hell yeah. So I took a 10-minute break, and what we're going to do is we're going to figure out this dimension. And I just realized we are a long way to make these, look nice, but at least we're going to get, we're going to use what we know to find this dimension right here. And it's good to have grid paper because a lot of these things kind of come out nice. One is we know this angle coming in. So this is how I like to do angles, is like, we have a grid here, and then we have this angle. And then so wherever we think that it's coming in, let's say it hits this intersection right here, we're just going to do another little grid. And these two, we can see that these two, and so I said this is S1, this is angle 1, S2, angle 2, S3, and this would be angle 3 over there. But this is going to be a mirror. Like, if these two lines are that should be the easiest and obvious thing to see when you have that. The second, I think of it like almost as a Z, where you have like this pattern coming in like that. You know what I mean? So anytime I see this Z, I'm like, hell yeah, I definitely know this is 1 over here. And then I can do that same process of like, oh, okay, this is 1. And so this is the triangle that we're interested in. Because we have this point coming in, and then we have these. So it's this triangle, and if we knew something about this triangle, whether it's the angles and stuff, we'd be just good to go. And with grid paper, this is helpful because this point hits perfectly right there. This is going to drop 1 and then go over 2. So if this is 1,000, we're going to drop 50 over 1,000, drop 50 over 1,000, drop 50 over 1,000. So we're just right there. And then so the distance here is going to be 2,000. So that's what I have. So from there to there is 2,000. Now if I know something about the angles in here, I can figure out, and then I guess just a take-home point is like, hey, I'm going to find out this angle. This is the angle that I'm able to find out. Because I know this dimension. And then if I know this angle and this dimension, this is the hypotenuse. Hey, the sun is shining. This is the sine component. So 2,000 sine of this angle, so that's what I have. 2,000 sine of this angle will give me the right dimension for that. Okay, so I know that, and what did we say this was? About 26 degrees. So I know that angle. Now same thing over here. This is going to be a 45-degree angle. I can do that same thing. It's like, heck yeah, this angle's 45. But let's take it all the way up here to our intersection. Do this little thing. And, hey, since this angle right here off of this 45 is, that's the same thing as that angle. So I'm still interested in this triangle. And now I know what this angle is. A composition of 1 and 2. And let's see, how do I know this angle up here? Same thing. I'm going to take this all the way up to this point, draw, the x and y. And here we have kind of that Z formation. I think Zorro or whatever, but that's just me. Anyway, so we have 2 over here, and then we have a 90-degree angle. So I know that this is 90.
So this whole angle in here has to be 90. I said that wrong. This is a 45-degree angle. This is 45, and this whole angle is 90. So we have 45, or we have 90 minus this 45. So this has to be 45. So nice. So we know this angle of the triangle, this angle of the triangle. Any triangle has to add up to 180. So I'm going to take 180 minus 2, 2, 1. Cool. And I did that. I got like an angle of, I stored that as alpha r. We got an angle of 63. So we did 2,000 sine alpha r, and we get 1,780. So this is 1,788.9. We guessed 1,791. We were just a little bit overestimating. Okay, now probably the more interesting way to solve, for a component, and I'm using a dot product. I don't know if I'm using in the simplest way possible, but also from geometry of this problem, I'm going to take this point of the box, so now I can probably bring out the problem. Alright, so this point of the box, I'm just going to call, a value of 0. 0, 0, and then we had 3,000 over to where this one came in. And we said that the intersection of this line and this line was just 500 up. So now we have this point being over 3,000 and then up 500. So that's all I did to do for that. And then we know this distance, it could be the square root of 3,000 squared plus 500 squared. That's going to be that distance. Because we have components of 3,000 over, 5,000 up. Pythagorean's theorem, this side squared plus that side squared, square root that is going to be this hypotenuse. Cool, but before that, what we have is, so we figured out that this is 3,000, I didn't even write it right, over 3,000 up 500 in the j direction. So we have I hat, j hat. The x direction, y direction, and that's going to be the components from this point to that point. What we're interested in is how do we, okay, so here we have this. So now we have this. This is our hypotenuse. This is the component we really want to know. So if this is the hypotenuse of this right triangle. Cool. We have to get to this a little bit later, but I know, and then all I have is the coordinates. And let's see if I did this right. Holy Toledo. Okay, so no, this is interesting. So this vector from here, the distance vector from here to here, is written like this. It's written as 3,000 over 3,000i 500j. It doesn't mean that it's that's just like the recipe for this vector. So if I wanted to know the magnitude of this 3,000i 500j, I would take 3,000 squared plus 500 squared, Pythagorean's theorem, and then the square root that to get that distance. Okay, yeah, so I think I'm going to clarify that, because it might be confusing when you're just like, well, is this two vectors? Is this 3,000i and then up 5, you know what I mean? No, this is the recipe for this vector. So there you go. So this 3,000i plus 500j is just one vector. It's this vector, and I even have letters, so it could be the vector v to f to d. So maybe this is vector fd. Starting at F, going to D. What we can do is the dot product along any other vector. I could just choose an arbitrary, a vector this way. Cool. And let's say this vector this way was 100 units long. well, I would have to, and let's say I had components this way and this way in my directions of like 90 and 30. Cool. To get a unit vector, I would have to say this direction is 30 divided by 100, and this would be 90 divided by 100. Cool. And if I did that, I would have 0.3 and 0.9. So you could, and then if I had that, then this would be a unit vector of 1. And we're pretty close. 0.3 squared plus 0.9 squared, square root that. Definitely this needs to be like 0.95. 0.95 squared plus 0.3 squared, square root that. Hell yeah, we get pretty close. Okay, so 95. Okay, hell yeah. So now we kind of know what a unit vector is. Now how could we, why when we dot this vector with, and this now would be well, it would be over in the, it would be negative 0.3i and then plus 0.95j. So why when we dot this 3,000 plus 500 into this vector, like what does that mean? Well, it would mean that, and I think it's actually going to be really difficult to even see, because this is just a little bit more than 90. Bummer. How would I even do that? If this is more than 90, I would have to take it this way. Yeah, so it's kind of fascinating. You kind of just draw a line of action right here, and then you go from this point, and then you try to just to get to the closest, like the shortest distance possible. So it might be, it might be like that. So the way I have this drawn, this might be the shortest distance to get to that line. And what the dot product says is if I take this vector and dot it with that vector, I am going to, now I'm kind of curious to do this. Because when with a dot product, you do get a scalar, but what you also get, you could get a positive or negative. So the way I have it drawn, because if I drew this as my unit vector, let's say it's this, then this is the shortest distance to there. And so what we would say is we're going to take this distance and it's shadow onto this vector. Even though this is a unit vector, that's just useful because when we do a dot product, you're essentially taking the magnitude of this vector and multiplying it by this vector. But we don't want to multiply, we don't want to get like two things multiplied together to be like this bigger thing that's nonsense. You know what I mean? So if we multiply this magnitude by 1, cool. Now we're, now we still have, basically you're still getting this magnitude. But with the dot product, you're only getting the components that are kind of shadowed down this. So it is the, I think I'm going to throw in the towel. It's, it's the cosine component. I mean, it's if I'm taking a vector and especially dotting it with a, anytime you're taking a vector with a magnitude, dotting it with a unit vector, because it has to be like a vector of like magnitude of 1, but in a particular direction, then you're treating this as the hypotenuse, and you're figuring out what the component is in that direction. So literally the magnitude of that is just going to be cosine, it's going to be this hypotenuse cosine of the angle. Alright, so man, and I could probably do more videos on that. I'm going to throw in the towel for explaining it anymore, but hell yeah. So let's try it out on the one we're actually doing. Well, I'm kind of curious about this one. Yeah, let's try it on this new one. So we have, and how a dot product works is, so we have 3,000, this component, 3,000, multiplied by the unit vector, its I component. So we're going to multiply by negative 0.3. Okay, now moving on. Now we're going to add. It's a scalar, so you just keep adding these terms. So now we have 500 in the j direction for this one. We're going to multiply it by 0.95 in the j direction. Cool. So once we do that, now we get negative 425. So yeah, so if this vector, this vector is about 3,000, 4,000 long, maybe a little bit, maybe just 3,000, just over 3,000. So keep that in mind. So this is 1,500. This is about 500. So it says that our component is not in this direction, but it's in the negative of that direction, and it's a magnitude of 425. So it's just right like that, and then we got a visual representation of that. Okay, so let's do the one that we're trying to find. We're trying to find this one, but we have to do it in two parts. We know that this vector is 3,000 over 500 up, and we're going to dot it in the direction of this vector. We know that this vector is a 1, 2, square root of 5 triangle. So this has components like this unit vector on this thing. If we did a vector this way, the unit vector would be down this way, and then over that way, and it would be down negative 1 divided by the square root of 5 in the j direction, and then it would be over 2 square roots of 5 in the I direction. And then that's the easiest way to do a unit vector, is to figure out, just any vector along that line. If you know the vector along that line and you know like its direction, then you can divvy it up into its components. This isn't a unit vector because 1 is a component, 2 is the other component, and 5, this is almost like 2.1 or 2.2. So to make this a unit vector, you have to take all these components and divide it by 5. And that makes sense from how I teach sines and cosines. Like, sines and cosines are percentages of the hypotenuse. So if and anytime your hypotenuse is 1, your sine and cosine components are those percentages, or are those fractional percentages. So to get that fractional percentage, I have to take this 1 and then divide it by the hypotenuse. Take this 2 and divide it by the hypotenuse. So cool. Hopefully I'm over explaining that and it's useful. Okay, so here's what we're going to be dotting. So we have 3,000, and the dot product's kind of weird, but as long as you know its mechanics and visually know what you're representing, we're taking this 3,500. But this vector, it's not two vectors. It's just one vector in that direction, and we're dotting it with this. And the dot product is a multiplication, but again, if we multiply by a unit vector of 1, we're not scrambling, anything. If you took this vector and multiplied by a vector that was even 5 units long, well, cool, you would just multiply this by 5, but then also it would only have a component, it'd be bizarre. But hell yeah, so you have to get a unit vector in this direction. Now it's not just taking this and multiplying by 1, because when we take the dot product, I think it's from like a weighted average or something. Yeah, that's kind of fascinating. I don't know exactly how that works. Oh, yeah. But it is. It's like I don't know if it's a weighted average or, Because if I have this as my vector, oh no, this is not going to work out. So this vector has an I and a j coordinate. This one also has like an I and a negative j. Cool. If I was to if this unit vector had the same dimensions, cool. I would just be multiplying by 1 and everything would come out, the component in that direction would be 100%. Now, when you're at a perpendicular degree angle, you get 0% in that direction. So even though we have skewed paper where this is 3,000 this way, this is 500 up, well, to get a perpendicular, if I was going down 3,000 and then over 500 this way, I would get a perpendicular. And if I took that unit vector and I dotted it with it, just the way the additions and subtractions, you would get 0. So that's the kind of the rule of the dot product. If I have a unit vector that's perpendicular to the actual vector, well then that means that this is the shortest distance. And so it's good to know like what that actually means. Alright, heck yeah. So what was I talking about? Yeah, so if I have this vector, 3,500, 3000i, 500j, and I dot it with a unit vector in a particular direction, where when I do the dot product I get 0, that means that this is the shortest distance. And I mean, it means it's the shortest distance from here to here, and it's perpendicular. I guess perpendicular is the most important part of that. It already means that, yeah, the direction that you had your unit vector, it means that your vector that you're dotting is perpendicular to that. And when you get a value that's not just this, when you get a value that's anything different, it's going to be somewhere in between. If I know that this vector is like 3,200, let's just say, well, I need to almost figure that out. 3,000 squared plus 500 squared, square root that. Oh yeah, it's really close to 3. Yeah, so we're just 3,050. So I know that this vector is 3,050. After I do that vector dotted with a unit vector in some particular direction, hell yeah, I'm going to get this distance. It's going to be smaller. So then what do I do? Like this is the most important thing that's like, usually people can get to there, or I'm just speaking for myself. Like I was able to get to that far, but then relate it back to how that works with this right triangle. I'm going to take that magnitude, or that now it's a scalar. So after I do the dot product, I get this distance. Cool. So let's take that distance right there and then divide it by the magnitude of the hypotenuse. I already know that's the bigger number. And what's that going to give me? That's going to give me the percentage of the hypotenuse in this direction, which is the definition of the cosine. Cosine says, like, hey, if I know this angle, cosine of this angle, which just means the cosine of this angle also just means, like, hey, if I know this triangle, it just means that this component, if I'm talking about this angle right here, and I know its angle in degrees or whatever, radians, take the cosine of it, it's going to say this side is going to be a percentage of the hypotenuse, a fractional percentage. Cool. All right, so now let's do it for real. So we have 3,000 multiplied by the I component here, which is 2 divided by the square root of 5. Cool. So, and now we got to just keep adding the component. We have 500. Now we got 500j multiplied by a negative 1 divided by the square root of 5. Okay, so this is our value. This is the dimension for this. I stored that as alpha h in my calculator. So just right up here we have alpha h. So that's this dimension. It's not the dimension we want, but this is, you know what I mean? So at least at least, you know what I mean? We got one of the dimensions of the triangle. We know this height. We know this, so now we're good to go. We know the dimension of the hypotenuse, and we know the one of the sides of a right triangle. So, I mean, this one you need to have. Pythagorean's theorem says a squared plus b squared is equal to c squared, but it's very good to know that, well, I don't know both sides, but I do know what c squared is. So I can say c squared minus a squared is equal to b squared. And that one should be intuitive. If I'm saying this side squared plus this side squared, that's going to be a bigger number. Is this side squared? Well, if I know the bigger number, then I'm going to take that, the hypotenuse squared. So c squared minus a squared is b squared. Cool. So let's do it. So we have, and I stored this as m. So that's going to be that 3040. So we have alpha m squared plus this dimension was alpha h in my calculator. Take the square root of that. And, oh, damn it. What up? Let's see. Let's do this again. After all that, I did it wrong. I said, you can't, is this squared minus this squared. So holy Toledo. So we got alpha m squared minus alpha h squared. So minus alpha h squared. Square root that. And hell yeah, we get the answer we want. 1788.9. And that's that dimension. Cool. So we did that dimension 2 ways or 3 ways. We did it graphically. We got pretty close. And then we just, had all the lines come together, figured out that angle, and we're able to figure out. So this was the triangle that we got. And then we knew one of the sides. So 2,000 sine of that angle gets us that dimension as well. All right, hell yeah. So, but now I guess the road to figuring out how to get this in terms of that. Holy Toledo. I might have to spend another 10 minutes kind of looking at how I want to approach that, but I'm up for the challenge. This is the least, I don't want to do it at all. You know what I mean? But we'll try. Just because some of these get real complex where I kind of do them in a long format way. So I just feel like I'm going to have a hard time simplifying down. But maybe I won't. Alright, so I'm going to give it a go. I'm going to take a little break. Catch you on the flip side. Alright, hell yeah. So we're back at it. And I'm pretty excited about this because I think I have a strategy to get to an answer like this. There was a couple things that I realized is that I think the red herring was making all of these 2,000, 2,000, 5,000, because your answer's simplified. So where do all those big numbers go? Well, it's the fact that these are just distances, and so when you're taking some of the moments, they are going to cancel out. You're going to take this force, which is a component of L, so we're going to have L, and then we're just going to have components in either of these directions. So again, this 45-degree angle is like a 1, 1, square root of 2 triangle. So the component this way is going to be 1 divided by the hypotenuse multiplied by L. Cool. And then, but if you do that, you're going to get 1 divided by the hypotenuse. That's going to be the component in this direction. So we want to rationalize those and make sure all the square roots are upstairs. So that was kind of the first thing. And then the second cool thing, let's get back to, because then when we do this, it was just real simple. And I just realized we don't even need some of the forces in the X or Y to start out with. Maybe in the end you could, maybe that'll be helpful, but we'll see when we get there. But what we do have is still this component we're going to bring all the way up, and we're going to bring this 45 to here. So because we have a 3,000 millimeter gap here, we're going to go 3,000 and up 3,000. This distance is 2,500, so we're going to be another 500. I scratched that out. We're just going to be 0.5 meters. So now just think of all these as, hey, this is 2 meters, 5 meters, 2 meters, 1 meter, 2.5 meters, 2 meters, 3 meters, kind of and so forth. And I think that'll be pretty helpful. Alright, so now we have the coordinates for this point. You know, maybe I'm going to set this as 0. I'm going to go over 3,000 and up 500. You know what I mean? So we can still refer back to this as 3,500, but over 3, up 5. So that's where I have here. Over 3 in the eye, positive 5. That's going to be this vector. And what we're most interested in is because when we sum the moments about this point, I forget what I called it, like, did I call it point D? All we're going to have is this S1, but we need this perpendicular distance. So then I did a very roundabout way of saying that if I know the unit vector in this direction, I can multiply this vector, 3i plus 0.5j, dotted with this unit vector to get this distance. And then take this squared minus this squared, square root that, we'll get that. But, man, you know, obviously this has a direction, and it's very easy to get the perpendicular. So that's what I did here. I just said, hey, this is a 1, 2. Let's draw a perpendicular line and see if we know anything about it. Because if we do, then we can figure out a unit vector in this direction. So that's what we're doing. And so this, this vector starts here, goes 3,000 up 5, or 3.5, I'm sorry. And so now we'll use this unit vector right here. So we'll figure out a unit vector right here off this one. And we know that this one is over 1 up 2. And it's going to be a hypotenuse square root of 5. So we know the component, the unit vector component this way is going to be 1 divided by the square root of 5. And then the upward unit vector is going to be 2 divided by the square root of 5. So now, hell yeah. Now we're going to do the dot product. We take this 3.5, so 3i plus 0.5j. And we're going to dot it with that unit vector. We're going to, and did I even do it right? Damn it, I don't even think I did. I got it backwards, so I'm glad I caught that error. So we're going to dot it with 1 divided by the square root of 5i plus, and then we're going to go up 2 divided by the square root of 5j. I did say we might want to rationalize these. That's going to be multiplying by square root of 5. You know, we want to multiply by 1, but square root of 5 downstairs, square root of 5 upstairs. So it's going to give us square root of 5 divided by 5i. Plus this one, same thing. Square root of 5 up and down. We've got 2 square roots of 5 upstairs divided by 5. And this is what we're going to dot. So, yeah, so we're going to have, when we do the dot product, we just multiply like terms and then keep adding them to the other multiplication of like terms. Cool. Alright, so we got 3 fifths, so we got 3 square roots of 5 divided by 5, plus, now this is just a half, so we have a half, this 2 is going to cancel, so we have square root of 5 divided by 5, so we got square root of 5 divided by 5. Hey, this is going to give us 4, oh, excuse me, this is going to give us 4 square roots of 5, and yeah, I did like, yeah, when you're, yeah, rationalize the numerator, and then it's just fractions. You know what I mean? And as long as you have the same thing, you know, you could factor that out. You could say that's the square root of 5, and then it's just 3 fifths plus 1 fifth. Okay, that's 4 fifths. So we have the 4 square roots of 5 fifths, or 4 fifths square roots of 5. However you say that, that's going to be this distance. And it just looks a little bit different because we divided everything by 1,000. So let's type that in my calculator. 4 square roots of 5 divided by 5 times 1,000. And we get that value, I don't even have, yeah, I took that graph graph paper somewhere else. So yeah, we're just gonna we know what we're doing, and we're just gonna dive right in. So yeah, that is our distance there. So now we're gonna set up our moment equation, and it's gonna be real simple. I mean, we do have the components here, but we know that the components are gonna act through the point, even though they act around the pulley. We know those same components are just gonna act right through that point. So it's kind of a fascinating one. And I guess let's talk about it again, because we have a line of action of this force, a line of action of this force. The resultant is going to go right through that point. So it honestly doesn't matter where you start. We could start it right up here, which just means that you had a huge pulley, and then you had a force this direction and a force at a 45. And the line of action of the force is going to be right through there, and that's where we already know the line of action of this force is going to be a 22.5 degree angle, and that's going to be, I don't even know how you would do that as a fraction. I don't know if you could, but anyway, yeah, is that something that we would want to try to get? I don't know. Yeah, what is the inverse tangent of 22.5? Did I say that right? No, what's the tangent of 22.5? Yeah, it's not a nice number. It's 1 minus the square root of 2. Is that right? 1 minus the, square root of 2 minus 1? Oh, that's cool. So I learned something new. I don't know why that's the case, but maybe this will be helpful. So the tangent of this angle means, you know what I mean? Like, so if we do this, it's going to be this side divided by this side. So this side is going to be 1 divided by the square root of 2, and this side is going to be 1. So that's the ratio that we have. So this is 0.4142, and this is 1. We'll see if that's... Oh, I can't imagine that's going to be useful at all. Because we would still have to figure out what the magnitude of this is. And I don't even think I want to do that. But we have this L. Like this component is L. And this component, the tension in this rope, is also L. The resultant is down this path. Yep. So yeah, let's not do that. But we do know that the line of action will be right anywhere along here. So we can put the origination of that point anywhere along this line of action. Is that something that I'm learning? Or is that not true either? No, I mean, obviously it's going to go through that point for I think the reasons that we talked about with the pivot and the pulley. You know what I mean? Okay, but hell yeah, let's scratch that, but we're going to take the moments about point D. We're going to use the fact that we already know that this is in compression. We're going to trust them on that. This one's going to be in tension, and then this one is going to be in compression. Okay, so when we sum the moments about this point, we're going to have S1, positive S1. So we're going to have S1, and then the distance is going to be 4 square roots of 5 divided by 5. Cool, that's going to be a positive moment. We're going to get 2 negative moments from here. We're going to get, so they're both going to be due to the load L. So I can factor out the load L. One of them is going to be the distance. Well, no, damn it. That's not true. Okay, so this one is the full load L, and it's a distance of 2,000. Or 2. So we have 2L That's it on that one. Now this one is going to be a distance of 2.5. So we have plus 2.5, or that's going to be 5 halves. Now it's only going to be the 1 divided by the square root of 2, which is the same thing as the square root of 2 divided by 2. So we're going to have the square root of 2 divided by 2, L, and cool. And so we have 5 square roots of 2 divided by 4. This is going to be 4, no, it's going to be 8 divided by 4. And that's also 8, yeah. Anyway, this is going to be 8 divided by 4 plus 5 square root of 2 divided by 4. Cool. Okay, let's do it. Yep. So we have, but you know, something I can see right off. No, never mind. Oh, I guess what I was. We'll do this in a couple steps. But yes, we have 8 divided by 4L plus 5 square roots of 2 divided by 4L over here, and then we have this over here. Now I'm going to. I thought this 4 was going to cancel. No, we got to divide by 4, so these become 16. So I have divided by 16. That's where this comes in. And then this 5 goes upstairs. So, and then the square root of 5 goes downstairs. So let's do this all in one step. So we would have 5 upstairs, square root of 5 downstairs, but we're going to get the square root of 5 downstairs, square root of 5 upstairs anyway. So we're going to have 5 square roots of 5 divided by 5. I don't know if that was worth rationalizing it, but I'm sure it is. And then, yeah, that's going to be S1. So S1 is going to be... Oh, man. So we're going to take this and then FOIL that through. Yeah, so we're going to have L. I guess we could factor out an L. We're going to have 40... Oh, wait, holy, this is 5 square roots of 5. Why didn't I see that? The 5's cancel. Duh. Okay, so cool. So this is just square root of 5. Booyah. So now we're cooking. So we have 8. So I see. They multiplied everything by the square root. So that's where that square root of 5 comes from. So right there, square root of 5. We have... They get 9 square roots of 2 plus 8. I get 5 square roots of 2 plus 8 divided by 16. So I'm off this 5 square roots of 2. Something was up where this is 9. So let's go back. Bummer. I should be using more paper, but at least we're on the right track. I mean, we almost got one of the solutions. Like I'm rushing through this because I would just never do this. So I think I can maybe slow down just a little bit. We can probably just redo this. I mean, it's not that hard. And I'm gonna just double check that this angle is right. You know, if we go down 1 over 2, then this angle perpendicular is going to be over 1 up 2. This distance is 3.5, so we have 3i plus 1/2 j dotted with 1 divided by the square root of 5 Yeah, I'll do it. 1 divided by the square root of 5i plus 2 divided by the square root of 5j. Multiply top and bottom by the square root of 5, and that's going to be the square root of 5 divided by 5i plus 2 square roots 5 divided by 5j. When we dot this, we're going to have 3/5 square root of 5i. No, and then when you do the dot product, you just get a scalar. So all the vector components go away. All right, and then the j is going to be 1/2. The 2's are going to cancel, so for sure. But we have the square root of 5 divided by 5. All right, so I'm sure I made the mistake right there. No, maybe not. Yeah, and then we have 1/5 plus 3/5. That's going to be 4/5 square root of 5. That's that distance, and we already double checked that, so we're good. We were good on that term. When we sum the moments about this point, we're going to have a positive moment. S1 times 4/5 square root 5 is equal to the negative, both of these negative moments. And we're already 3,000 over, so we're 2 more to get to there. So we got 2, and then this is L. That's it. Like 2L down. Cool. This one is going to be 2.5. So we got plus 2.5. But I'm going to write it as, is this where I went wrong? 5/2? No, so we're good there. 5/2 L. And then the component in that direction is going to be 1 divided by the square root of 2, which is the same thing as the square root of 2 divided by 2. So that's going to be the component of L in that direction. So we have the square root of 2 divided by 2. All right, sweet. All right, so this term is going to be 5 square roots 2 divided by 4, L. This term is going to be 8 divided by 4L. So I'm doing the same thing. I don't know. I think it's decent. And then we can multiply both bottoms by 4 to get 16. So we got rid of that. And then we're going to divide by the square root of 5, multiply by the square root of 5. This is the same thing as this, which is 5 square roots of 5 divided by 5, which is just the square root of 5. And did we do that right? Square root of 5 was downstairs, 5's on top. Rationalize, we get square root of 5. So we're multiplying by the square root of 5 here. I still don't see where they get 9 square roots of 2. Oh, holy hell, my bad. So I was thinking one of these canceled. So that's all right, you know what I mean? It's kind of the first big mistake. But you could make a mistake like that and then just never come back to it for days. So I didn't realize that this vector has 2 components that are adding to the magnitude of the moment at D. You know, I thought it was just one where it's just only this component and we cancel the other one because I thought we already did it. No. These are 2 different vectors this is L that way, but this has a component that way too. So we got to redo that setup. So but we do know that this is going to be 4 square roots of 5, So we got 4. So we have S1, 4 square roots of 5. Okay, sweet. So we know the moment is going to be this force times this distance. Those are going to be the positive moments. They're going to equal the negative moments. Let's see what we have. We have this component down. We also have this component has a component that's also down that way. And then we have this component also has a component that way. Cool. So now we're cooking. So this first component is going to be a distance of 2. So we're already over 3. We got to go 2. So we got to go 2L. That's the first component. The next component is also 2. So we got to go plus 2. But now it's just a portion of this. It's the square root of 2 divided by 2L. Cool, so that's what we have down. The 2's cancel. Okay, so that was that component. Now we got the other component in that direction. So we got plus, this is going to be 2.5, or 5 square roots of 2. We have the square root of 2 divided by 2L. That's due to that 45-degree angle. And yeah, now we can start to add like terms. So this is going to be 5 square roots of 2 divided by 4. This is going to be 4 divided by 4 square roots of 2. So there you go. There's the 9. That's going to be 9 square roots of 2 divided by 4. So there you go. Check on reality there. And then we're going to add it to 8 divided by, did I do that right? 8 divided by 4. 8 divided by 4 is 2. And so both of these are L's. The 4 is going to come down here to make this 16. And then again, we're going to take this, and then, so then if we bring this to the other side, you got 5 on top, square root of 5 downstairs, but we're going to rationalize it. And this becomes 5. That cancels that 5, and we just have the square root of 5. So we're going to multiply all this by the square root of 5, and we got S1. So, whew, that was brutal. But there is just no way on earth that I would ever want to sit down, or I just don't want to be. I like doing it the way that I did. I like spending 5 hours on this problem, going from an analytical perspective, just guessing, getting to here, where it's just like, oh, hell yeah. So it's just like, hey, I can see these two vectors come together. I'm going to sum moments about that. I need to know this distance. Cool. That's going to be the dot product of this vector in that direction. Well, I should say this distance vector. This is going to be this distance vector, which I do know, and it's going to be in that direction, and I have those components. And so, cool, we did it. So let's see, and then we did all the rationalizing, which is a good skill. It's not a skill I was ever, like, in any classes where, I mean, you know, as an engineer, I just don't think, I don't know. We were never required to do anything like that. I think it was just more, let's learn concepts and move on.
All right, hell yeah! I better save some juice. We only got like 4 minutes of
battery Anyway, so yeah, we still got to chisel down on this. So what do we have here? So we have S1 is equal to, and it's going to be a negative. We already said it was in compression. That's where the negative sign is. Mine's positive. I just showed it in the negative compressive direction. But we do have this square root of 5. Cool. We do have the L, I guess, outside everything. We have this 9 square roots of 2, and we're going to add it to 8. and we're going to divide everything by that 16 multiplied by L. So yes, we got it. We got the right answer from that process. Okay, now the next thing, so we know what S1 is. We still just can't sum the moments in the Y and the X, because we still have, no, we can. Yeah, so that's pretty cool. So even though we know S1, but this is kind of cool, because we can, if we sum the moments in the Y, we know both the X and Y components of this. We know both the X and Y components of this, or of this Pulley system. This has a Y component. This has a component in the Y that, so these both have components in the Y that we don't know. But this has a component in the X. And that's the only component in the X that we don't know. So this is pretty sweet. So now I can let's do the components in the X. I think that would be the most logical thing to do, hopefully. I mean, we could also just start summing moments about this point as well. No, we would have to sum the moments about this point to get SE like we did before, but I don't know. Let's try summing the moments in the X direction, because this one goes away, and it's just on the pulley. It's just one component in that direction. Yeah, let's do it. So S2 will have a component in that direction, the negative direction. Well, I'm already saying it's a negative, so that's the other thing about this. I'm claiming it's in tension, so I have it drawn the right way. So we will get a positive answer for this one. Well, we're getting positive answers for everything. We're just showing. I mean, this is redundant. Negative compression. I don't know. You know what I mean? Maybe not. It depends on what your arrows look like. Like if they're saying this is a compression and they're putting a negative sign on, they're assuming tension. You know what I mean? So you've assumed tension and you got a negative sign, therefore compression.